Okay, welcome everyone. This is Michael Gibbs from Go Cloud Architects. How are you all today? In any case, I'm super happy and super excited to be here with you today. Today, we're going to be talking about one of my favorite topics in the entire world, networking. So for those of you that don't know me, my name is Michael Gibbs, and I'm the founder and CEO of Go Cloud Architects. And we're an organization that's really dedicated towards building high-performance cloud computing and networking careers. The network is the heart of everything. It is the foundation, it is the plumbing, it is the basis of everything that we do. And if the network doesn't work right, nothing works right. And when the network works great, everything works great. And you know, the best part of the network is no one even thinks that it's there. So when you've got some network skills, you're really in a great place because you're one of the few people that actually knows how it all works. So because of that, we're going to talk about networking. I've been involved in the networking field for a really long time. I went from practicing internal medicine to senior network engineer to lead architect in about 6 months when I began my tech career transition 25 years ago. And during this time, I've been working in networking forever. I got to work for companies like Comcast as a principal architect. I got to work at Cisco as an enterprise architect for almost a decade, and what a great experience it was. I got to work designing systems for banks, and it was great and I love it. And networking is the foundation, and I want to give you that knowledge, and that's why we're here. Now, the specific part of networking we're going to talk about today is subnetting. And while everybody thinks of subnetting as the foundation and the basic, most elemental part of networking, which it is, it's also one of the most critical parts of networking. In fact, where people make errors in networking, the people that do the network design and the IP address design should be the most senior people out there. Why? The way the addresses are laid out and the way the addresses are planned will determine if the systems will work now or will work ever, or whether they're going to run into problems as the systems grow and scale. So networking, specifically the addressing plan, will determine how everything works on the network. And we're going to spend a lot of time on that. So we'll talk about subnetting today, which is basically taking one set of blocks and breaking it down. We'll talk about classful addresses, which we don't use anymore, so we can get into classless interdomain routing. Then we'll talk about what goes into subnetting. Then we'll talk about how to subnet. Then we'll actually go the opposite direction. And in the opposite direction, what we're going to do is we're going to talk about how to supernet, which is used for route aggregation and route summary. Then we'll do some practice things and we'll work through it together. And then if you guys want, we can add some architecture to the mix because we know I love architecture. And if you guys want to add some architecture to the mix, we can design an enterprise with their subnetting. And if you want, we can even put in a routing protocol or two. And I can teach you how you would design a system, maybe with a core access distribution. If you want to do some network architecture in there, we'll have some fun. But we can't do any network architecture. And quite frankly, we can't do any cloud architecture unless we've got the IP addressing down. So that's what we're going to talk about today. We're going to have some fun, and it's going to be there. So if you guys are having fun and want to do some tech and want to do some architecture, please, in the chat box, do this. Type networking for cloud computing. I'm hoping to see a good 50 of them because there's 46 of you on here right now. And also, if you're ready to have fun, if you can hit the like button, if you're not a member, if you can subscribe, if you're a subscriber, if you can hit that bell, you'll be notified because we've got a lot more free training initiatives coming out for you. So networking for cloud computing, I'll know that you're here. So hello, everyone, and welcome. And while you're popping that in there, I can see actually who's coming. Abigail Marks, Cloud Hired. I'm so happy to see you here. Marla, I'm doing great. I hope you are too. Pierre, so good to see you. Hi, everyone. Leo, so good to speak to you. Youssef, so happy to see you. Leonard Lash, I'm doing great. And my cat Cindy's doing great today. She's been a very sweet little girl. Millicent, Cloud Hired, see you. Leo, hello all. Nitropan, great seeing you. And Noel, it's always good to see you. Theo Q, welcome. Hello. Chad Perez the Des, love some architecture. We'll do some architecture. Alonzo, my really good friend, who I call James Bond. Cloud Hard, good to see you. And Perez, networking for cloud computing. David, welcome. Marla, welcome. And Daniel, I'm so happy to see her, Daniel. So good to see her today. Let's get everybody cloud hired. So, networking for cloud computing, super happy to have you here. So let's talk about IP addressing and what it is and how it works and why all of this stuff matters so much. Balwinder, wonderful. Carlos, wonderful. So happy to see you, Yusuf. It makes me so happy to see so many people coming from all around the world. IO, I know a lot of IOs, but IO, I'm super happy to see you here, regardless of which IO you are, or if you're another IO, still thrilled to see you here, Christina Lee. Welcome, welcome, welcome. So let's get in to subnetting. And before we do this, let's talk a little briefly about IP addresses. Now, every device in the entire world, if it's going to be reachable, has to have an address. And the addresses are all going to have to be unique. So, you've got a phone. Somebody wants to call Go Cloud Architects. They call 973-896-4889. And then either I'll answer it or the phone will be forwarded to one of my executive team or somebody else will hold the phone. And how does the phone company know to send that call to that +1 973-896-4889? How does the world know it? It knows it because the phone companies have switches. And the switches basically have a map of basically the network, and the switches know where to send the calls to. Well, guess what? When we're dealing with computers and we're dealing with network and communication, here's what happens. We've got these devices called routers, and routers actually build a map of the network. And what goes on is they know how to get from point A to point B, and they route or route your traffic through the network. But what are the routers actually looking at? What is the routers building a map of? They're building a map of all the subnets along the way and which interfaces to use to actually get to which subnet. So every device is going to have its own unique address. And every device that's on a subnet can only talk to devices on that subnet or on that network. To go from one subnet, and we'll talk about what these subnets are and things later, to another subnet, or a class B address to a different class B in a different network, you need a router. So that's the key element to all of this thing is what is networking? Networking is basically connecting devices. Networking provides the plumbing. Every device needs a unique address. And the address has to be on the same network as the other devices that it's talking about. And when we talk about the same network, we're actually talking about the same IP block. And we'll get into that. So let's first start with what is subnetting. Subnetting is basically the process of taking a big IP network, and we're going to work on that, and I'm going to show you exactly what, where, how, and why, and breaking it into smaller components. So think of subnetting as pre-virtualization. I take a server with 128 cores, and I chop it into 64 two-core servers. It's just like subnetting. Subnetting, I can take a block that gives me 16 billion or 16 million addresses and chop it into a whole bunch of blocks that give me 250 addresses. So think of subnetting as basically virtualizing or chopping a big subnet or a big network into littler ones. Now, why do we do server virtualization? To conserve servers and maximally utilize them to get the best utilization. Why do we subnet? To conserve IP addresses and use them maximally. So here's a couple of secrets, and I'm going to show you why. When you're dealing with a server, or you're dealing with a router, or you're dealing with a firewall, every interface has to be on a different subnet. So if you've got a server with 4 network cards, they all need to be on a different network or a different subnet. So that is what we're dealing with. So let's look at this architecturally. Let's talk about if, for example, in this particular environment I'm going to show you right now, over here, we have a router. It's got 4 subnets on it. Now, each subnet, because it's got 4 interfaces, like each arm on a router is an interface. So what'll happen is, let's pretend I'm the router in the center. And let's pretend my left arm over here sees the 3 subnet. My right arm over here sees the 1 subnet. If traffic comes into me, the router destined to the 1 subnet, the router knows to take it from where I'm at, send it through my body, and send it out my right hand. It'll reach the right subnet. And then the traffic would go back the same way. So that's the way the routers know what to do. That's the way the routers know how to send these things. So now let's pretend, for example, every interface on the router needs to be on a different network. And the answer is, we do. So Now let's look. If we used a /8, which is a class A address, and we'll talk about these addresses, each class A address, basically subnet, basically gets 16 million addresses. So for example, if we did this, if we put 16 million usable addresses on one port on the router, 16 million usable addresses on another port on the router, 16 million usable addresses on another port on the router, and 16 million addresses on another port of the router, I would have used 64 million addresses for a single router. I got to tell you, you want to know how many IP addresses we have? We have 2 to the 32nd minus 2. So wasting 64 million addresses for a single router would be kind of horrible. So now let's talk about why we subnet. So now instead of wasting 64 million addresses, what if I could create a subnet that only has 4 usable addresses? Well, actually, total 4 addresses, of which 2 are usable. And all I needed to do was a link from point A to point B. So I need one address over here and one address over here. I don't need any other addresses for the subnet. So here I've subnetted my big networks down, and I've chosen to use 16 addresses total for my 4 interfaces on the router. Now, granted, I've lost some addresses because we'll talk about it later, the subnet address, the broadcast address, and other things. But in this particular picture before, my router is using up 64 million IP addresses. In this situation, with a little careful math and planning, I'm using 16 addresses. 16 versus 64 million. Now, look at the number of IP addresses we have. 2 to the 32nd minus 2. It's not that many. We ran out of IP addresses a long time ago. So because of this, that's why we subnet. We have no choice. Subnetting enables us to take a big block or a big network and chop it down into little ones. Now, what we're going to do is we're going to work through a lot of examples of how we do this. And I'm going to give you lots of projects. And then after we do the subnets and we work on the subnet design, things that we'll do after that, for which case we're going to have a little bit of fun, are going to be as follows. After we do the subnets, then we'll design the architecture, show you how the architecture, and show you how all these pieces and parts actually are going to fit together in a way that's going to make sense for you. But we've got to start somewhere, and I just wanted to start by showing you those things so you understand why we subnet. So now that you know why we subnet, let's walk through the first part of something that's part of our history. And if you don't know this history, you won't be able to understand classless interdomain routing. And we're going to have to talk about this because I want to make sure you know it. So let's begin with this. Let's talk about IP address classes. So when I started my networking career about 25 years ago, we were getting out of something called classful networking. And now we're completely out of something called classful networking. But what is this concept of classful networking? If you actually go into the IP addressing history, you'll see that we had 5 classes of IP addresses. And we had the class A addresses, the class B addresses, the class C addresses, the class D addresses, and the class E addresses. And for the most part, other than class D addresses, which are used for IP multicast, we don't really use any classes at all. But what is an IP address class? Well, anything where the first octet, meaning the extreme to the left, was between 1 and 126, and the subnet mask was a /8, that was called a class A address. And if you're dealing with real networking people like me that have been working in, you'll often find people just refer to a class based upon the subnet mask, which is not actually accurate. So you might hear me call any /8 a class A, but it's really only if the first octet is 1 to 126. Now, a class B address is going to be that 128 to 191, and it's going to be a /16, which is basically 16 bits. And we'll show you exactly what it's going to work out mathematically to network bits and ultimately 16 bits of host bits. And then we had the concept of the class C address, and these are your /24s, but they were between the 192 to all the way to 223. And then we had our class D addresses, which are used exclusively for multicast, and that's 224.0.0.1 all the way through 239.255.255.255. That's your class D address. And then realistically speaking, your class E addresses were experimental. They've never been used for anything. So now you know the type of address classes we're talking about. And now that you know the address classes that we're talking about, let's kind of start walking and looking through. So if we actually go back to this architecturally, and apologies for hiding behind so many slides today. I like to be right out there front and center with you, but today there's just some things we've just got to visually present. So apologies for all these extra slides. Typically speaking, this is a class A, the top over here. And the reason it's a class A is a class A has 8 bits of network and 24 bits of host. So when you get that 10.0.0.0.0 /8, you're getting those .0.0.0. Those 3 things, that's your 24 bits of host masks that you can actually use, as opposed to the network bits, which are just the first part. So realistically speaking, that's what we're kind of talking about. Our class B addresses are going to be balanced. They're going to be 16 bits of host, and they're going to be 16 bits of network. And our class C addresses are going to have 24 bits of network and then 8 bits of hosts. And by doing that, ultimately what you'll see is we're going to run into an issue of addresses. So 24 bits of host and 8 bits of network as we're dealing with class A. When we're dealing with class Bs, we're dealing with 16 bits of networking and 16 bits of hosts. We'll just modify that. I'm not really sure how the graphics got this way, but apologies. And then ultimately, we'll have 24 bits of network mask and 8 bits of host addresses that we're dealing with in this section. So now you can see what's kind of going on. Now, that was classful routing. Now, the concept of classless interdomain routing is a little different. We're basically saying we don't have to stick with these bits, these pre-programmed bits. We can chop this down any way we want. And that's really what it is. So instead of a class A being 8 network bits and 24 host bits, what if we could move the network bits over? Maybe we have 24 network bits and 8 host bits, or maybe we have 16 bits and network host bits. What's going to determine that? Well, how many hosts do we need per subnet? If I've got a point-to-point link, meaning a wire on both sides, and each interface has to be on a different subnet, I can never use more than 2 IP addresses on both sides of a WAN link. Never more than that. So my subnet should never be more than 2 usable addresses for that. So that's going to be a /30. But I might have another environment where I need 230 servers. So that's going to be a /24. So what are we going to do? We're going to figure out how many hosts we need per subnet. And that's going to be the way we're going to determine how we chop it. So you guys are all going to get good at math. If I need 2 hosts, I pick one subnet side. If I need 200 hosts, I pick a different subnet side. If I need 400 hosts, I pick a different subnet side. Want to know the secret to subnetting? Do you want to know the 2 subnets you probably remember in your head? And if you knew none others, you'd probably be pretty okay. We use a /30, meaning 255.255.252 for point-to-point WAN links. And you know what we use for LAN links almost exclusively? A /24, which is a 255.255.255.0. I will tell you later architecturally why those are the 2 that are chosen. I will show you why we do this, how we do this, and why it's the right choice for an organization, and 99% of the cases without even thinking about it. But I just want you to know that. But we're going to get into the math. We're going to get into the fun. Of course, we'll map it out architecturally. And then because it's networking, and networking can be fun, if you want to play with some BGP or OSPF, all these things along the way, in the end, we'll do it. So to let me know that you're still here, type #CloudHired in the chat box. I know you're here. I know you're all awake, alert, and oriented. And then we'll get on to some more fun. So please hit the like button. Tell others to join it. Tell others to subscribe. We work pretty hard to try and make sure we bring as much content as we can for you, especially free. So it's always good when the algorithms all see that people are happy and having a good time. So excellent, and thank you. So now I want to go into this concept of exactly what determines what we choose, when we choose it, and how to choose it. It is the number of hosts that you're going to need, for the most part, that drives your subnet size, the number of hosts that you actually need. So make sure you've got the right number of hosts in your subnet. And you also need to know the number of subnets that you're going to need. And that's going to give you your mathematical ability. Do you chop on one side or you chop on the other side? How many hosts do you need? Now, there is a formula to determine how many hosts. And I'm going to show you the good mathematical formula, and then I'm going to show you the I'm bad at math cheat formula. But in any case, I just need you to know how to do it. I need you to know how to do this, how to understand how it works. Look, once you get experience, you can build yourself an Excel spreadsheet or use any tool you want, but you have to know how to do this because it's super critical. So let's go to this environment. How do you know how many hosts are going to be available? Well, we're dealing with binary numbers. So basically binary is on or off, 0 or 1. So because we're dealing with a binary address, it's either going to be a 0 or a 1. 0 off, 1 on. Realistically speaking, that's it. So here's the cheat, and I'll show you in a minute. If you want to know how many hosts per subnet, the best thing for you to do is take the number of host bits to the exponent of host bits, and I'll show you what I mean by that, and subtract 2. But I'll show you another cheat way too. So if, for example, I'm going to make a /30, I've got 6 subnet bits, right? 8 host bits, because we borrowed some. 6 subnet bits, 2 host bits. So in a /30, how many will I have? 2 hosts. So it's 2 times the number of host bits. So 2 times 2, which is 4 minus 2. Okay, wait. Now instead of a /30, let's say I chose to use a /29. Okay, so now that's 5 subnet bits and now 3 host bits. So in this case, if I want to figure out how many hosts, it would be 2 to the 3rd, because I've got 3 host bits. 2 exponent number of host bits gives me 8 minus 2 equals 6. Okay, now instead of doing a /29, I want to do a /28. How many hosts do I have? 2 to the 4th. Why 2 to the 4th? I've got 4 host bits and 4 network bits. So 2 to the 4th, 2 to the 4th host bits gives me 16. Minus 2 gives me 14 usable addresses. Now, there's something goofy about AWS and some of the cloud providers. We'll talk about that later. But I want you to get the Subnet Mask first. Instead of a /28, we choose to use a /27. /27, oh wait, that's 5 net. That's how many host bits? 5 sets of host bits and 3 sets of network bits. So now 2 to the 5th is 32 minus 2. And that's what we're dealing with. Here's how we're actually doing it. We're dealing with 2 to the number of hosts minus 2. Now, when we're dealing with AWS, we're going to have to deal with some other funny business. AWS decides to reserve the first 4 addresses of a subnet as well as the last. So realistically speaking, with AWS, it would be 2 to the x minus 5 as opposed to 2 to the x minus 2. And when you're dealing with the cloud providers, they all have something goofy with their addressing schemes. So just please remember theirs. I'm teaching you the regular networking thing that's going to work on your Cisco router, your Juniper router, your Palo Alto device, your Fortinet device, or everywhere in between, and what's going to be going on in an organization's data center. And you're going to have to deal and contend with both. So you need to know both. And that's why we're spending so much time and effort on this, because it really matters. So that's why we're dealing with these things. So let's walk through the math. Now we'll get into the nuts and bolts of how this works. So let's say here we have a class B. And what does this look like naturally over here? Let's say this was a 172.16.0.0/16. This is what it started out as. This is where we begin. So, that's where we begin. Now then, that's going to get subnetted down. And how do we subnet it down? As it stands right here, we've got 16. A class B is going to have 16 network bits and 16 host bits. So if you want to know how many hosts would be in a subnet for a class B, it'll be 2 to the 16th minus 2, which is a pretty big number. It's like 65,000. Now, if we don't need 65,000 hosts in a subnet, and guess what, everybody? You can't put 65,000 hosts in a subnet. In fact, you don't even put 1,000 hosts in a subnet. And the reason you can't put that many hosts in a subnet is as follows. All your computers do this. I'm here, I'm here, I'm here. ARP, 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 broadcast. I have this service, I have this service. They broadcast. Computers, they chat, they get talk in the subnet, and they fill up the subnet with traffic. The servers and the systems have to process the broadcast traffic. It sends the CPUs to the ceiling. So you can't put that many servers or computers in a subnet anyway, because these computers, especially Windows devices and Apple devices, they send all these broadcasts and they constantly fill up the system. So the point is, you can't put that many hosts in a subnet no matter what you'd want to do, because the hosts themselves will actually fill up too much. It's like putting so many people in a room. If you had 100 users in a room, it might be okay if the room's big enough. But if you put 1 million users in a room, you're not going to hear anything, because the people are going to be talking so loud. If you wanted to have a polite conversation with someone next to you, you wouldn't be able to. So with your systems, you're never going to put more than 500 systems in a subnet. And the reality is, you're almost never in your life going to put more than 250 units in a subnet. So your normal LAN subnet mask is going to be a /24. And your normal WAN subnet mask is going to be a /30. But there are times where you need to do more, and we're going to have to route aggregate up and chop down for routing purposes. So you need to know how to go in all different directions. So now, 16 bits is subnet of network mask, 16 bits of host mask. But let's say we choose to borrow 8 bits of host mask and give it to subnet masks. So now what do we have? Let's go back here. Where was I? Bear with me a second. So let's go back to this situation. What this looks like, if we don't subnet this down, all these are going to be zeros. This is what we start out with. This is what it's going to look like initially. That's our class B address. And we decide to subnet it down, and we make these subnet bits. So now let's say we've got these subnet bits and we change them all to 1. Let's make sure I've got 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. So now, what does this look like to you? This is a /24. Why is it a /24? It was a /16. So we have 16 bits of network bits. Now we have 16 bits of subnet bits, which get counted towards the network side. So they get shifted towards the networking. So now we have the 172.168.0.0/24. We subnetted it down. How many hosts can we put in the subnet? Now that it's a /24, 8 bits a host. 2 to the 8th minus 2. Come on, everybody do it. 2 to the 8th. 2 exponent 8 on your calculator. The number you get is 256. Minus 2. How many does that give you? It gives you 254 addresses. Want to know the cheat way to figure it out? If, for example, you know your mask. So let's say, for example, you take 256 bits. So let's say, for example, you take 256, and let's say we go back to that /30, which is -4. 250, that's going to make it more complicated for you. I have a cheat approach to math, and then the cheat approach worked well for lots of people. But maybe let's just keep it focused to the main approach. But you'll be if you take 256 and you subtract your basically your hope is you'll ultimately get to the same destination. But let's keep it simple, and let's keep me all on one formula, the standard formula that it's going to work everywhere instead of the old network engineers formula. So just let's keep subnetting it down. So let's extrapolate this into another environment. I want you guys to all understand this. /24. And if it's at 172.16 or 172.168, doesn't matter. It's still a /24. But in this particular environment, let's say we've got 255, 255, 2550. This, by the way, is traditional subnet mask. Now, what you see over here is something called Cider notation. So what is Cider notation? Cider notation is for people like me that have been working with classless interdomain routing for a while, and we just think of terms of bits. So realistically speaking, you could look at this subnet mask as 255.255.255.0, or you could look at it as 24 bits of network mask. It doesn't matter. Now, what this is, which is the same as this, mathematically is all ones for the first octet, all ones for the second octet, and all ones for the third octet. Now, that's what we see. This is physically what's going on, mask-wise, bit-wise, but this is what it's actually going to look like when you would type it in. But this is actually what it would be referencing in terms of bits of subnet mask. Look, 8 plus 8 plus 8 equals 24. Now, let's say we wanted to shrink the /24 down to a /25. Here's what we would get. It'd be the same ones, ones, and ones, but here we're going to go one direction over. Hey, Arun, so good to see you, Cloud Architect. And so again, that's going to be popping in. So now let's say we want to add 2 bits of subnet mask because we want a /26. And as you notice, as we shrink down this way, our subnets are going to get a lot smaller. They're going to get much smaller. So now we're going to add 2 bits of additional subnet masks over the traditional class C. So now it's going to be 255.255.192, and I'll show you where those numbers come from, and it's a /26, etc., etc. Now, here's an extreme one, something that only network architects like me will ever see, and this is called the /32 subnet mask. This is a host mask, just a host root. So for example, those of us that are putting loopback addresses on routers, lots of us use a /32. Why? It wastes no IP addresses, but this is something that nobody will ever use. You can't use it outside of a loopback address on a router, so kind of get that out of your mind. So, okay, are we all ready to get started? Let's do this. Let's work through this all together. So when we're dealing with subnetting, what are we going to be dealing with? We're dealing with the network bits. We're dealing with the host bits. Now, with every network, we're going to have something. We're going to have the addresses that need to be tossed away. So let's talk about the addresses that need to be tossed away. There are, in normal networking, the first address of a subnet is used by the router or as the network number, and the last address of the subnet is used for broadcast, meaning send something that everybody else can see. So I need to make this clear. So let's, for argument's sake, let's say we take a /30 subnet. Let's say we've got a 192.168.1.0/30. This is the subnet. What the routers will use to put in the routing table is they will have a 192.168.1.0/30. This will be the route, and that's going to be the subnet. Then we will have the 192.168.1.1/30. That will be used by, that's one usable address. We will have the 192.168.1.2/30. That's a usable address. And we're also going to have this 192.168.1.3 address. Now, this .3/30 is a special address. It's called a broadcast address. And what makes this address so special is this is what the routers keep in the routing table. This. And that's how they know where the subnet is. So this can't be assigned to a host because it's used by the router. This is assigned to a host, meaning one side of the link. This is assigned to another side of the link. Now this here, this all ones broadcast, that says something that can be seen to everybody. So if I send a ping to 192.168.1.1, 192.168.1.1 is going to respond with an ICMP echo reply. If I send a ping to 192.168.1.2, 192.168.1.2 will reply to me and say, got it, Mike. Now, if I send a ping to 192.168.1.3, here's what's going to happen. The 192.168.1.1 and the 192.168.1.2 will both respond to the ping because I sent a broadcast which is, hey, everybody, answer me. And everybody says, I hear you, Mike. I'm answering you, Mike. So that's what's going on. So that's where we look at these things. So the first address of all subnets is used by the router. The last address is used by the broadcast. Now, if you're with AWS AWS actually reserves the first 4 IP addresses and then the last one, which means, could you use a /24? I mean a /30 in AWS, except for the link on the way to get there. Well, /30 is 4 addresses. AWS reserves 5. You can't use a /24. I mean a /30. In fact, a /29 would also be problematic because that would give you what? It would give you 2 to the third, which is 8 minus 5 is 3. Again, you'd be in trouble. So the smallest subnet you can use with AWS is a /28. Now here's the thing. Best thing you could possibly do, LAN segments /24, WAN segments /30. You don't have to think about it as much that way. Generally good things if you can do that. But, keep these things in mind. So now, I want you to all, with me, we're going to do some subnet math. We're going to look at these random addresses, and we're going to figure out, where does the subnet begin? Where does the subnet end? What are the usable address ranges? And what's the broadcast address? So here's how we do this. So if any of you guys get some CCNA math problems, see this on an AWS exam or a Google exam, it gets pretty easy. Let's do it. So let's do this. 192.168.1.132. Okay, somebody show me what those 25 bits of subnet masks looks like in the chat box. And so put it in octets, 1.1.1.1.1.1.1, etc. dot 111 dot, etc. Somebody show me what does 25 bits of subnet mask look like in both Cider notation as well as decimal notation. I'll tell you what, I'll kick it off in decimal notation, and somebody else show me in binary notation. Decimal notation, it's going to look like 255.255.128. That's what a /28 is going to look like, everybody. So I'll pop it in there. Now, I want all of you guys to show me that mask in subnet bits, or at least somebody, the first person that does it, gets the gold star for the day. Show me what that looks like in binary notation. David Page, excellent job. Perfect. You showed it to me exactly in binary notation. Caroline, excellent. Jenny, almost. Only 1 bit of subnet mask in the last, not 2 in the last octet. Asim, great job. Okay, this is good stuff. Arun, excellent. I'm so happy to see you here, Arun. Abraham, excellent. Jazz. Well, we're going to have 8 in each box, but yeah, I figure that's your shorthand. But yes. Anson, excellent. Excellent. I'm super happy to see that. Okay, so now let's have some fun with this. And Broderick, it'll be the same, but we're going to have 1, 1, 1, 1, 1, 1, 1, 1, 1 dot, because it'll be 8 each time. Great for you, old time honey official. We're doing great. I'm really excited. Love seeing this. I love watching people do a really great job for the day. Fantastic, everyone. So now let's go back to play with our math. So now in this particular example I was giving everybody, let's go back and let's have some fun with it. So now let's figure out where this subnet begins. Here's the secret. Make yourself this chart until you get used to it. 2 to the 8th is 128. 2 to the 7th is 64. 2 to the 6th is 32. 2 to the 4th is 16. 2 to the 3rd is 8. 2 to the 2nd is 4. 2 to the 1st is 2. And we'll just ignore this whole one thing over there. So let's think of it this way. So now, 192, 168, 1.132. Where does that fit? Well, let's now go to our cheat sheet. Does it fit inside of 128? Is 132 divisible by 128 in some way, shape, or form with a number that is greater than 1? Yes, it is. So does 128 fit into 132? The answer is yes. So the subnet for this first one is going to be, can anybody tell me where the subnet begins? I'll do it with you. 192.168.1.128. That is the subnet. Note, it's a /25. That's where the subnet begins. Where does the subnet end, everybody? The subnet's going to end at 192.168.1.255. What are the usable addresses? Everything from 192.168.1.129 all the way to 192.168.1.254. So these are kind of, one of the things that I want us to do, that I want you to understand. So I have a couple thoughts. We're going to do a math problem or two here. I'll open it up for some questions. We'll do some more math problems. We'll open up for some more questions because I don't want anybody to be lost. So if you guys have any questions, start asking them. What'll happen is Chris from my team is going to aggregate them and say every 15 or 20 minutes from now on, we're going to come off mute and answer your questions because we're going to build on this stuff relatively fast once I know that everybody gets it. And we're going to get into some architecture and some things that could actually get potentially advanced today if you guys catch up on the math. So let's make sure we answer any questions. So now let's do another math problem. For this /27, let's say 172.16 1.27/27. So what is 27 bits of subnet mask look like? Well, for one thing, it's going to be 255, 255, 255 plus this plus this plus this. That's going to be your subnet mask. So what does that look like? 128 plus 64, everybody. What's that? 196. Add 32. What does that get you to? 224? So there's that. So let's go back to this. So now let's say we're here. So okay, so now working on this assumption, where does this subnet mask go? Where does this subnet begin? 172.16.1.128. We've got, this is the mask. Anasim Hands, excellent, you've got it. Jazz, excellent, you've got it. That's what the mask looks like. Excellent, excellent, excellent stuff. Super happy to see this. So now that I see this, here. Now what do we do? And Christina Lee, I'll show you how the people calculate it so quickly in a second. They don't have to do too much thinking about it. So Christina, the reason it's so fast is we know we've got 24 bits. So that means the first 8 bits are all ones. It means the second 8 bits are all ones. It means the third 8 bits are all ones. And then we've got 3 more bits and we go from right to left. From left to right when we calculate them. So the point is 24 bits will always be 8 ones. .8 ones, .8 ones, .zeros. The /25 will always be 8 ones, .8 ones, .8 ones, .11, and the rest zeros. /30 will be, for example, always 8 ones, 8 ones, 8 ones, .6 ones with 2 zeros afterwards. So realistically speaking, that's what's going on is people are just looking at it saying, okay, I just remember 1 bit, 2 bit, 3 bit, 4 bit, 5 bit, 6 bit, 7 bit. And when you just remember it that way, it just sort of clicks in your head. So let's calculate this one. If we know the mask is going to end in a 224, and how many addresses do we have in a 224? Well, we can take 256 minus 224, and how many addresses does that give you? For one thing, 256 minus 224, that gives you 32. 32 minus 2 equals 30. Or do you want to know how many addresses you could do? You could do 2 to the 5th minus 2. It'll still give you the same addresses. So now let's look at the subnet mask. Everybody, where does the subnet mask begin? 172.16.1.27. Where does this thing start? Okay, is it divisible inside of 32? The answer is no. But that's how many bits we have. So we know this subnet begins with 172.16.1.0/27. That's the subnet. That's the beginning. So now let's figure out where it ends. What is 2 to the 5th? 2 exponent 5th, everybody. 2, 4, 8, 16, 32. So that is your broadcast address. 172.16.1.31. Why is it 31 and not 32? Because we start counting at 0. 0 to 31 equals 32. 1 to 31 equals 31. 0 to 31 puts us in these kind of positions. So that's, realistically speaking, that's how we calculate these things. So now this means that our subnets, the usable addresses in our subnet, are going to be 172.16.1.1 all the way to 172.16.1.30. And then this will be used by the router. This is what's going to be put in the routing table. Try and get this. This will be in the routing table. This will be the broadcast address, and these will be the address that are usable for your hosts. Let's do one more. Now, let's do this. Let's go to this 192.168.1.17/28. Okay, everybody, what's a /28 look like? Let's go work out those bits. It's going to be 8 bits plus 8 bits plus 8 bits plus what? 4 more bits /28. 8 plus 8 plus 8 is 8 times 3 is 24 plus 4 more. That gives us 28. So tell me here, where is this subnet going to begin? In /28. Is 17 divisible by 16 more than once? And Pierre, great job. I'm loving it. You're correct. Asim, excellent. Ronald, awesome. Cloud Fresher. Caroline, excellent. Anson, Tom, excellent. Alex Wood, excellent for the last octet. You got it. You got that last octet. Exactly. Christina Lee, excellent. Femi Power, okay, this is making me really happy, really proud. David Page, you guys got it. You guys are doing amazing. Okay, I'm just so happy. This is going to make my day. I'll be in tears by the end of the day if you guys all get subnetting and supernetting. You guys get this right, it changes everything. So I'm so happy for you guys. Okay, so now let's do this. Let's go back to this address. Somebody tell me where the subnet begins and then where it ends. So we now know from the math that you guys all did that 17 is divisible by 16 by at least 1. So that means this subnet is going to begin at 16 in this particular case. So let's go up here. And now let's start with the first IP address. It's going to be 192.168.1.16. That 16 is the network mask, meaning it's used by the router. That is the network, which is used by the router. Now, somebody add 15 more to this 16, and then we know what the broadcast address is going to be. It's going to be 192.168.1.31. This is the broadcast. So now, what addresses are usable? Somebody tell me what addresses are usable. Type it in there. In between the .16 and the .31. What are those addresses? Somebody tell me in the box. What addresses are usable? Someone give me a range, like a dot something to a dot something else. Pierre, I hope it clicked. Old time official, you still don't get it? That's okay. We're going to do a few more of them for you. Evo 17 to 30. Asim 17 to 30. Now, Amrath, I'm real happy that you're coming off of mute and you're putting that in there. Excellent job, Amrath. Very happy. Okay, so good. So let's ask this question again. So Abraham has this question. It's a really good question. And I know we talked about it, but let's talk about it again. How do we determine the number of hosts per subnet? Well, very simply, we do the following. We determine the number of host bits. And then from there, we just do 2 to the exponent of the number of host bits minus 2. And then we get to our answer. So let's say we have a /24. If we have a /24, how many host bits do we have? We have 2 exponent 8 in your scientific calculator, which gives you 256, minus 2 gives you 254. Now let's say instead of a /24, for which case we've got 8 host bits, we've got a /25. How do we determine how many hosts we have in a /25? We do a 2 to the 7th because we've got 7 host bits. 2 to the 7 equals 128 minus 2. That means you've got 126 hosts per subnet. So now, the next thing you might want to know, what would your next subnet look like? Let's say, for example, instead of the /25 we just talked about, we have a /26. That means you're going to have the /26 is 26 network bits and 6 host bits. So we do 2 to the 6, which is 2 times exponent 6 on a scientific calculator. 2 to the 6th gives us what? 30 or 64. I think 2 to the 6 is so 2 to the 7th is 128, 2 to the 6th is 64. So we do 2 to the 6th, which gives us 64 minus 2. Now let's say we want to shrink it down even some more. So instead of that /25 or the /26, we want to use a /27. So now we've got 5 host bits. So that's going to give us 2 to the 5th, meaning 2, 4, 8, 16, 32 minus 2, or 2 exponent 8 in your scientific calculator. So that's pretty much it. That's how you're going to determine how many host bits. So the next question is from Pierre, and it's a great question. How do you determine the starting address? Now, this is something a lot of us put on interviews because this gives us the answer if somebody understands this. So let's work through it because it's a great concept. So Pierre, this one's going to be all on you. And I'm going to have you respond to this in your own time. And I know there's a delay, so take your time. So here's what we're really talking about. And anonymous YT, we can't just use a calculator. And see, here's the thing. What happens when people just use a calculator is they're having something else that does the math for them. But the problem with that, anonymous YT, is the people that are using the calculators for the math, if they don't understand why the subnets are being designed the way they are and why they're being laid out the other way, then they're just using math that works. And if we don't know to design the IP addressing scheme and where the IP addresses need to be in the network, it will negatively impact the routing. And I got to tell you, in about 25 years of networking, we'll say about 80% of the problems that I've seen are from people that actually use subnet calculators because they actually didn't understand the networking design they were going to do, put the wrong IP addresses there, which messed up the OSPF, the BGP, the intermediate systems to intermediate systems, and then everything basically piled onto the bad foundation. So I'm not going to say I like math. I hate math and anonymous YT. And I'm not going to say I haven't built myself an Excel spreadsheet that I would use for an IP addressing plan that I use for all my systems. But I build it based upon the network and the systems based upon the designs. So you realistically need to know how to do this. Plus, the ability to work without this is going to be really challenging. So I want you to be really strong in this because I want you to have a good career. Without it, it's going to be near impossible. So let's try and deal with this. So Pierre, let's go back to the octet piece. So if it's a /8, we already know what it looks like. If it's a /16, we know what it looks like. So let's just do these masks one more time. So let's work through this. So let's say, for example, we decided to use, let's pick this one. We're going to use a /28. So first, let's map it out here. 1, 2, 3, 4, 5, 6, 7, 8. That's 8 bits. Assuming I did my math correctly. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So 8 times 3 gets us 24. Now let's add 4 more bits, Pierre. And then the rest are going to be zeros. So now we know over here exactly what this is going to look like. This is the subnet mask. Now, Pierre, if you want to know where it starts, Jenny, I'm a CCIE. My CCIE number is 7417. Cisco taught me to use a /30 for point-to-point links. And you can't use a /31 for a point-to-point link because you don't have anything for the network and you don't have anything for the broadcast. So however that got misinterpreted, I don't know. But Cisco only says /30s. And when I was at Cisco, that's how they taught us to do it. And when I worked and trained systems engineers at Cisco, on Cisco Systems Engineer TV, we always use /30. So I don't know about the /31 because it just won't work. So unless they added a new feature that would enable it to break routing or traditional routing. and which I've not configured the routers for a couple of years. But let's go over here. So we've got our 8 bits, our 8 bits, our 8 bits, and our 4 bits. So now let's look at this. So where are our 8 bits coming from, PR? So we've got a 128 plus a 64 plus a 32 plus a 16. That's what our mask is going to look like. Now, let's go back to this /28. What you really want to do is you want to see if your things are divisible by the mask. So, for example, if you are here, is 19 divisible by 16? And the answer is yes. If 19 was if 19 was not divisible by 16, let's say, for example, in this environment it was 08. If the subnet is divisible by 16 and it's not greater than 16, we're starting with the first subnet or the 0 subnet, the beginning part of it, and then we're going to be working our way all the way up to 15. Why is that? Because this number is the number of bits we have, and the number we had is less than that, so it's going to start at 0 and work its way up to 15, which is the broadcast. Now, Pierre, let's pretend this was 49. Is 49 divisible by 16, Pierre? Yes, it is. It is divisible by 3 times plus the number 1. So if that was the case, Pierre, the subnet would begin at a 48. Now, it would begin at 48, and it would go up 16 more. So that would be 49, 50, 51, 52, 53, 54, 55, 56, 57, 58, 59, 60, 61, 62, and 63, because remember, we start counting at 0. So that would be my 15 plus the 0, which equals my 16. Now, by comparison, Pierre, let's say it began with 78. Is 78 divisible by 16? Sure it is. 4 times 64 is 4 times 16 is 64. 5 times 16 is 80. So we know we overshot it with 80, Pierre. So let's go back to 64. We can look at this subnet and say this subnet begins with 172.17.1.64 and add 15 plus that, which means we know where the subnet's going to end. It's going to be 70, it's going to be 64 plus 15, and that'll be where your subnet ends. So that's really how we're doing that. Pierre, did that make sense to you? If not, and if other people need that, let's go back and do it. I want to make sure everybody gets this. Could you guys help me out and let me know if you got it? If you got it, type cloud hired. If you want me to cover it again, say cover it again in the chat box. Just so I know.
Did you want me to bring in any other questions?
If we got questions, yes. Although it looks like some people want me to cover this one again. So let's make sure we cover this one more time. Okay, can I go over the host bits if we go over more than one octet? Okay, so let's go back and look at this one more time. Our bits are going to be counted in octets. With IP addresses, we have a 32-bit address, which is covered by 8 bits and 4 octets. So a /8 mask looks like this. So if that's a /8, a /16 looks like this. And I'm not counting my zeros, so I could potentially be typing too quickly or missing one. And a /24 looks like this. Anytime we add networking bits, we go in this direction. So if we want to go to a /25, it's going to be this. If we want to go to a /26, all we're really doing is we're just moving over one more, and we're moving from left to right. But that's what's really going on. So now that we remove that from the equation, let's figure out, if you want to know where your subnets start, first you need to know where your masks, you need to understand the subnet mask. And then you need to understand how many hosts per subnet. So if we need to draw it back, let's go to this one, this 172.17.3.129. Let's first draw the mask so you can see what it is. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. That gives me 24, right? Now I've got 29. So 24 needs how many more? It needs 5 more. 1, 2, 3, 4, 5. 1, 2, 3. So now let's do this. Let's count over 1, 2, 3, 4, 5. So now we know exactly what we've got in this /29. And this /29 obviously won't work with AWS, but it would work in the rest of the networking world. So with these 5 host bits, where does this network begin? Well, I don't know. We're going to have to calculate it out. So we have 3 bits of host bits. What is 2 to the third, everybody? 2, 4, 8. What's 2 to the third, everybody? 8. Now let's go back to 19. Is 19 in some way, shape, or form greater than 8? Is it divisible by 8? Yes. If we divide 19 divided by 8, and the reason we know it's 8, because it's 2 to the third, because that's the number of host bits we have, 2, 4, 8. So now 19 is divisible by 8. How many times? 2. 9 times 2. So 19 is divisible by 8. How many times? 8, 16, 24. So greater than 2, but less than 3. So now let's think about this. If the subnet begins, if it's greater than 2 and less than 3, that's our subnet range, which means now let's think about this. Where does it start? Where does this 8 times 2 begin? So we've got a 172.17.3. What is that? Wait, if we've got multiples of 8 and it's greater than 2 and less than 3, what is 8 times 2, everybody? 8 times 2, because it's divisible by 2 as a whole number, is going to give us 16. Nitropan, that's exactly where the subnet begins. Now, the next subnet is going to begin, the next network is going to begin 8 numbers higher. So the next subnet is going to begin at 24. And then the subnet after that will exist at a 32. And then the subnet after that will exist at a 40. And then the next one will be a 48. So now let's going back here. Where is, and nobody messes, just because we all mess up a number, it's no big deal, Mark. I mess up lots of numbers. So now if it begins at 16 and then we know the next subnet begins at 24, where does this thing end? It's going to be the largest number that's not divisible by 3. So 24 is divisible by 3. What's that number that's 1 less than 24? Well, Alex, you're doing pretty good. 24 minus 1 equals what, Alex? $23, exactly. So the subnet will end 172.17.3.23. Good job, Alonzo. Fenny Power, Alex Wood. I can make a number off by 1, 2, or even a million and not even know it. So, you guys are doing great. I mean, this is networking. It takes everybody a little bit of time to do this. You guys are doing fantastic. And we're going to do this. We're going to make sure that you guys get it in broadcast. You're right. The .23 is the broadcast. Exactly. Exactly. So good. So let's keep doing this. Also, I'm being told that if you guys are having a good time, if you can hit that like button, subscribe. I'm also told I should remind you guys that on Monday, we're going to have a free How to Get Your First Cloud Architect Job webinar. And it's going to be a really, really great time. We're going to teach you everything you need to do to get hired. But I'm going to go back to the teaching. I'm learning how to use YouTube. So if you can hit the like button, subscribe, hit the bell, all these metrics that I'm supposed to know all about as somebody that spends some time on YouTube. But seriously, it does help our YouTube metrics, which helps us teach more people around the world. And we do a lot of free training, and it means a lot to us. So anytime you guys can share our message of free training to help others in the world, it really means a lot to us. So let's go back to here. Now let's go back to this situation, the dot 30. Okay, somebody show me. So what's this dot 30 look like? Well, let's go back and redraw our mask. We know the first three octets are all ones, right? And then we know we count from left to right. So dot 30 means we've got 24, so that's 25, 26, 27, 28, 29, and 30. Let's add 2 host bits, so we get to 32. So now, and thank you so much, NitroPan, we love having you here as well. And I love sharing knowledge and experiences. So now, let's go figure this out. We've got 6 bits of subnet mask, everybody. So 1 bit, 2 bits, 3 bits, 4 bits, 5 bits, 6 bits. Okay, here we go. Tom, excellent, you got it. So now, going back here, is 2 divisible by 4 with a number of greater than 1? No. 2 is not divisible by 4. I mean, it would be as 0.5, but it's not a whole number. So this subnet is going to begin. Tell me, somebody, where does the subnet begin? Given that 2 is not divisible by some number. So we're going to begin at the first subnet, and we're going to end at the last part of the first subnet. So somebody tell me where the subnet 10.0.0.something/30 begins. Well, tell me where the 10.0.0.2/30 subnet begins, somebody. Tell me the first address. Tell me the last address. Evo, this looks like something great for you because I think you're Miss Math, but Orpheus just got it. 0 is the network. 3 is the broadcast. 1 and 2 are the usable addresses. So exactly. Perfect. Tom, do you speak Greek by chance with your name? If you do, just say Yassas in the chat box and I'll know that you speak Greek. Otherwise, it's super wonderful having you here. I'm just always looking for more people to speak Greek to. So, okay, let's go over here. Let's do another one. So now we've got the 10.0.0.9/24. Everybody, /24. Now on our /24, for the fun of it, how many hosts? Okay, well, how many bits is it going to be? 2 to the 8th. 2, 4, 8, 16, 32, 64, 128, 256. Here we go. There you go. So, there you go. That's the number of hosts. 256 minus 2. Because remember, got to lose the broadcast, got to lose the subnet. You want to know how many hosts you have in AWS? 250, 2 to the 8th minus 5. Same thing. You just have to learn which addresses you're going. So going back to this one, going back to this 10.0.0.9, we're having our fun. We're doing our things. We're addressing our stuff, all kinds of cool. Let's go look. Now, where does this subnet begin? It's a /24, which means 254 usable addresses, but a total of 256 for the subnet. So is 9 divisible by a whole number into 256 or 254? No. Since 9 is not divisible by 254, for example, where does it begin? The subnet's going to begin, well, NitroPan, good job. Exactly, the subnet will begin with 10.0.0.0, and it will continue all the way to the broadcast address, which is 10.0.0.254, which means the usable addresses will be the .1 all the way to the .253. And the range that you guys have listed of 0 to 255 is perfect because 10.0.0.1 is usable by the hosts and 10.254 is usable by the host. The .0, like Amaranth said, is used by the router, and the .255 is used for the subnet directed broadcast. So you guys did it Perfect, 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 perfect. Now, we're going to give you guys one more, and then we're going to start going in the opposite direction. Why are we going to go the opposite direction? Because the opposite direction is routing. This direction is addressing, the opposite side is routing. And when we get this, and then we get the routing, we can speak architecture, and then we can map out some network architectures, which you'll see commonly in the network environments, the cloud environments. After all, cloud's nothing more than a network and a data center that's been virtualized. It's just somebody else's computer and somebody else's network when you take all the mysticism out of it. Now let's make sure, let's make this a little bit harder. Let's take this one and let's make it 40. Okay, so now in this particular 10.1.1.46/30, I made this one an ugly one because we're going to challenge your math skills. And if you're like me and you're Mr. Verbal and you don't like math, well, then let's just say you're going to think about this one. But you all got it, and it's not that complicated. So it is a /30, which means 30 bits of subnet mask. So 25, 26, 27, 28, 29, 30. Okay, so that gives you the number 4. 2 to the exponent of 2 gives you 4. So now, where does this begin? Is 46 divisible by 4? Yes. How many times? 12 times 4 is 48. 11 times 4 is 44. Okay, so where does this subnet begin? Tom Orpheus, Polioreo. It begins with a .44, that's the subnet. It ends with a .47, which is a broadcast, and .45 and .46 are the usable addresses. So you guys got it. You guys are doing great. I'm so happy. Give yourselves a round of applause. Pat yourselves on the back. You guys are doing really great. So now you know. This is good stuff, everybody. Super happy for you. So now we've done some really nice networking stuff. We've subnetted it down. Now we're going to have to go the other direction. Why the other direction? Why is the other direction so cool? Because now we're going to start talking about routing. Okay, so now let's think about networking. What do routers do? Routers build a map. They determine to go here, because to get to John's house, go out this interface. To go to Chris's house, go out this interface. To visit my cat Cindy, go over here. But see, routers don't think in terms of my cute cat Cindy. And they don't talk about, how to get to Chris's house. They think in terms of subnets. So realistically speaking, the routers are just building a map of subnets, and now you know. You and I and humans, we think of Main Street and villages and things that make sense to us. The computers just look at these subnets. And now, realistically speaking, what we're going to actually have to do is we're going to go start and we're going to supernet them. And for the question from Asin Hans, before we actually do this, and actually before we do this, let's make sure we address all the questions. So let's address the questions before we go into the next section. So the question from Asim Hans, how does the lesser number of usable addresses given play in the last example? It really doesn't change much of anything, Asim. So what it means is because of the way AWS uses addresses, you're not going to be able to use a subnet that's going to be smaller than a /28. But the math is going to be the same. The only difference is, normally speaking in networking, if we go back to any of these examples, let's say we go back to this example. Let's go back to this example over here, because it's a valid question. Let's say we go to this address over here, the /28. The first 4 bits are always going to be 8. The second 4 bits are always going to be 8. These 4 bits are going to be 8. And then we're going to have 4 bits of subnet mask here and 4 bits of host mask. So what is the subnet going to be on this, Asim? It's going to be the same one. Where does the subnet begin and what is going to be used by the router? Well, let's go to this environment. Let's say we go to this /28 that we just picked. So 25, 26, 27, 28. So now let's figure out what is divisible by 16. Is 78 divisible by 16? The answer is yes. 4 times 16 is 64. 5 times 16 is 80. So that means that the subnet's going to begin at 4 times 16, which is 64. So we've got this 172.16. .0. We've got this one. I'm sorry. 172.17.1.64. This is the subnet. Guess what the broadcast is? Add 15. 172.16.1.79. That's the broadcast. It's the same on either one. So see, none of this changed. Now, the only difference is AWS won't let you use .65, .66, or .67. So the addresses that you'll actually be able to utilize with AWS will be less because you won't, because this is going to be reserved. This is going to be reserved. And the next one's going to be, I'm sorry, I've switched from a Mac recently to Windows, and I'm still learning how to use Windows. Used either Linux or Mac for the last couple of decades. And all of a sudden I'm using Windows because my Mac couldn't handle my needs. And let me tell you, it's a change. So, okay, so we're here. So that's realistically speaking what's going on here is you still have the same subnet. You still have the same broadcast. You just can't use these three addresses. So assume it's not going to change anything. You just can't use these. So there's that. Now let's see. Remember what I told you. /30 is for WAN links. /24 is for WAN links. And when you're dealing with the /24, instead of having 254, you're just going to have 251. So it's really not going to be anything that affects you. So I hope I answered your question there. Before we move on, were there other questions on this topic? Okay, well, Sri, welcome. I love networking too. Now, let's go the opposite direction, everybody. Exactly, there's going to be less addresses because they waste them. So if there would be a total of 2 to the 4th, if you would typically get 2 to the 4th minus 2, it'll be 2 to the 4th minus 5. Same thing, NitroPen, you just get to use less of them. Now, what we previously did, everybody, was we borrowed network bits. We borrowed host bits we took the network and we added some more network bits to, effectively speaking, increase the number of, or to decrease the number of host bits to decrease the number of subnets as opposed to decreasing the number of hosts. Now, let's go the opposite direction. What if, instead of taking a bigger network and making it smaller, I could make a bunch of smaller networks look like one? Now, this is the point where you're going to be like, okay, great. Mike just taught me how to chop big networks into small networks to save IP addresses. And now he's going to teach me how to take these smaller networks and then build them back into a big network. Okay, so this is pretty important for you to understand. We maximize the use of IP address space by taking subnets and shrinking them down. We optimize our routing by minimizing the number of routes in the routing table and engineering our traffic where we use a specific interface for a specific subnet or another interface to go to a specific subnet. Now, the ability to determine whose traffic goes where and engineer your traffic is going to be explicitly based upon how intelligent your addressing scheme is. So remember, we've just gone this way. We've been moving in this direction. We've been adding network bits, and by doing so, we've been taking the host bits and creating network bits. Now we're going to go the opposite direction. Okay, everybody, how many hosts are available in this subnet? 192.168.0.0/24. So if you don't know, do 2 to the 8th minus 2 and tell me. $254, exactly, Pierre. Exactly, Mark. Okay, good. So now that you guys are getting it, I'm David Page, Ashley Hughes, Tom, Femi, Ashley, Excellent. Now, since I know you guys got that, now somebody tell me, Clayton, tell me how many hosts are going to be available in the next subnet up, 192.168.1.0/24. Again, it's going to be 2 to the 8th minus 2. So how many? You guys have already done the math. Just do it again one more time for me, just so I know you understand. Exactly. It's a class C, so it's going to be 254. So now this 192.168.2.0 is going to also be 24. And the 192.168.3.0 is also going to be a 254. You guys get it. Now, let's look at this. Now, if what we previously did, so let's go back and let's add some cool math in. We used to do this. So right now we have 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, now let's do this. This is the one subnet mask for the top subnet. Next subnet, next subnet, next subnet. Hey, wait, don't they all look the same? So now, can you guys all see this? Does everybody see that we've got 4 contiguous subnet masks? This octet is 0, this one is 1, this one is 2, and this one is 3. Does everybody see that? Okay, so now let's think about this. If, oops, this Windows computer, it takes some getting used to. It runs great. Got to say, AMD's Threadripper CPUs are pretty awesome. So, /24, oops, no, never mind. Apologies here. I did some little funny cutting and pasting. 1, 1, 3, 4, 5, 6, 7, 8. The third octet should be all ones. Thank you, Amrath. This is the danger of live. When you do live and you're doing your own math at the same time as you're typing, you do miss stuff. Something tells me, let's just make it over here. So if I've missed a number, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's looking relatively as clean as we're going to do for live. So now, /24, 0 and 1. Instead of this being a /24 and this being a /24, now what if instead we change this to a 0 and we change this to a 0? Now we have a summary address that looks as follows. We've got a 192.168.0.0/23. Does everybody see that? All we did is we went the opposite direction. Previously, we were moving our network this way. In this case, we're moving our host bits this way. So really all we did before is we took a /24 and we took a /24 and we aggregated them together into a /23. That's it. So now everybody, let's take these next 2 subnets. 192.168.2.0/24. And now this one, for example, is the 192.168.3.0. Could we then, because they're contiguous, meaning one right after the other, then switch this to a 0, then switch this to a 0, and now have a second /23 that looks like this, 192.168.2.0/23? Everybody see that too? Because all we did here is we did the following. We took these 2, we took this address, borrowed added a network bit. We took this address, added a network bit, added a host bit, I should say. And that came up with a /23. Now guess what we did over here? We took this one over here, took a extra host bit from the network, and created another /20. Now we've got 2 /23s. Does everybody see that so far? Because it's fundamental what we're doing. Ashley Hughes, you got it now. Now, right now, if I tell other people I have access to subnets 192.168.0.0, and I tell somebody else that on my router I have access to the 192.168.2.0 subnet, I've reduced the number of routes that I had to tell the rest of the world about to 2. But I can still reach all those subnets. And why can I reach all those subnets? Because this is inside of this, and this is inside of this. Now, this subnet contains this subnet and this subnet. Since all you guys see that now, I want to get more elegant. Can I now take this and this and make it even better? Go over direction one more. Can I now take 192.168.0.0/22? Just moving it over, which effectively makes my new mask look like this. Exactly. Joe White, excellent. Excellent, excellent, excellent. Ashley, excellent. So that's all we're doing with summary addresses. We're taking our subnets, and at least from an address perspective, we're aggregating them in something we can send out. So Carlos, with Fs, we're dealing with IPv6 because IPv6 is in hex. With binary and IP addressing IPv4, we're only using 0 to 255. There's no Fs in binary. Now there is at the MAC address level because that's hex, but not with IPv4. So now let's do the same thing 2 more times. So now everybody, 10.0.0/24, 10.0.1/24, 10.0.2/24, and 10.0/324. Can anybody think what we could do here? Could we roll up a /24, a /24, a /24, and another /24 into a / what? What would give us 4 of these subnets? We just did it, but somebody worked through this. Okay, so we don't need to make this scary. So they're contiguous. A /24 and a /24 combines into a /23, right? Okay. Now, a /24 here and a /24 aggregates into a /23, right? So we've got 2 /23s. We want to go up one. How do we aggregate 2 /23s together? What do we need? Okay, we'll do it all manually one more time. You guys will get it again. So, because you guys did it when I got it manually. Amranth, you got it. So if everybody else sees what Amranth sees, excellent. If you guys don't see what Amranth sees, let's work it through. Okay, Ashley, you got it at /22. It's exactly a /22. Daniel gets it. It's a /22. Excellent. So now we're going to make it harder. Well, I'm not sure I completely understand that, but we're going to make it harder. We're going to add a level over here. So here's how we're going to add a level. Now we're going to go from 10.0.0 all the way to 10.1.7.0. And guess what? It's not going to be that complicated. How many contiguous subnets is this? 1, 2, 3, 4. Well, this is the same one, so let's get rid of that. 5, 6, 7, 8. How many contiguous subnets do we have over here? We got 8 of them, right? Well, 2 /24s turns into a /23. 4 /24s turns into a /22. So what's bigger? What's double that size? /21, Amranth. Okay, well, Amranth got it. It's going to be a /21. Does that make sense to people? Pierre's got it. Blackjack, yep, that's the answer. So that's the answer. Why does AWS reserve a bunch of addresses for experimental uses? It's their choice. They've chosen to do it, and it's their system. So some of the cloud providers do it as well, but you can run your business any way you want. But given those experimental addresses aren't really being used, I don't think they're serving any purpose for anybody. How about the 10.1? What about it, the 10.1? So the 10, the 0, the 1. Oh, that was actually great job there, Tom. Tom, sometimes what happens is I draw my graphics and then I send them to someone who's much more artistic than me. Sometimes my graphics actually get drawn on a napkin. Sometimes they get drawn on a piece of paper, or sometimes I take a picture of something. So occasionally, some of the people that help me draw the pictures occasionally make a mistake, or I gave them a mistake and they couldn't read my handwriting because they're getting, doctor, nurse practitioner handwriting, which is pretty sloppy. So apologies for that. These things just definitely happen. So the second set, so the question is Asim Han /15. So a /15 would give you 2 /teens put together. 2/22s, 2/24 equals a /23. 4/24 equals a /22. 8/24 equals a /21. 16/24 equals a /20. 32/24 equals a /19. 64/24 equals a /18. 128/24s. Well, now the math is getting a little goofy in my head, but you get the concept. That's the way you aggregate it. It goes in reverse by bit one at a time, Asim. I hope that makes sense. So now, let's start putting the pieces together. Now that we're off some of this kind of goofy language, here's where it all goes wrong, everyone. We're going to now talk about how it should be versus how it usually is. The reason I make it clear and I say people should not use subnet calculators is not because I have an aversion to science. It's not because I have an aversion to tools at all. I love tools. I don't know how to use tools, but I love tools. I've got all kinds of hammers and screwdrivers from my friends come over because they impress me. They know how to use them. I wouldn't know at all. The 10.1. So if you had a 10.0 and a 10.1, those two could be aggregated into a /15 on the scenes. So yes, that would be a /15 if you were going to do that. The answer would be yes. But realistically speaking, when you have to do this, they have to be contiguous subnets. So let's talk about a bad addressing scheme. By the way, this is what I see all the time. This addressing scheme that I'm going to show you is one of the reasons that I will tell you that in my life, I have troubleshooted network after network. This is what happens when someone doesn't understand subnetting but uses a subnet calculator. They do this. And by the way, this will completely work until it falls apart. Move the stuff over. So this is something you're going to see constantly in your career. You're going to have somebody that's done this. They gave the data center these subnets, 10.0.0/24, 10.0.2/24, and 10.0.3/24, and they have 10.0.1.0/24 sitting in the cloud. They've got that subnet for servers. Now, if you've got 4 subnets, this is great, and you'll never have a problem. But the companies I work with have 40,000 subnets at minimum. And heck, some of them are connecting to internet service providers and taking in 750,000 subnets from 10 different internet service providers. So that's where these things break. In this case, we've only got 4 routes. We only need these 4 subnets. So plus whatever the WAN link is. So we've got nothing to worry about. But you're going to see a lot of this. This is a disaster. Now, what's going on here is right now, you need to send these 3 routes from the data center to the cloud. And the cloud provider will need to send this route over. Now, I want you to think about this. Does anybody know how many routes you can send to AWS from your data center? Total routes. It will only tolerate 100. 100 routes, that's it. That's all you can send to AWS. And it's not because AWS isn't a great cloud provider. And it's not because they don't have sophisticated routers. They only tolerate 100 routes, which is basically 0, because the reason they can tolerate 100 routes is they've got millions and millions of customers. And if they had to take in 50,000 routes from 10 million customers, there's no routers in the world that can do it. So they limit themselves to 100 routes so their systems can scale. The routing takes CPU, it takes memory, so they limit how much you can give them to protect themselves. Otherwise, we'd all be DDoSing AWS's network every single day by sending them standard networking. So they can't handle it. No cloud provider could handle that. No routing protocol could truly handle millions and millions and millions and millions of customers with thousands of routes each. So AWS forces you to cut it down to 100. And how do you cut it down to 100? You better be really good on your addressing scheme. Right now, we've got to send 3 subnets just from here to the cloud. Now, if this was addressed differently, that wouldn't be the case. Now, let's talk about doing it right. See, what you did here is you had the 10 address space here and you had it here, which means I can't send a single summary route. I can't send this route, which is what I'd like to do. I'd like to be able to send the cloud this route, 10.0.0.0, and I'd like to be able to combine this 24, this 24, this 24, and make it a single route, meaning a /22. Why can't I really send a /22 over here? Because part of that /22 is sitting on the cloud. Because whoever set up the subnets didn't think about it ahead of time, and they put part of this that should be here over here. Now, technically, it's still going to work right now, but if we scale this, it's going to fall apart. Exactly, we're almost sending the cloud a route to itself. Exactly, PR. Now, we've got more specific because it'll be directly connected to the cloud, so it'll temporarily work, but we're going to have routing problems later. Now, by comparison, if we were smart about it, this is the way we want to design it. So look at it this way. By doing this way, we've got a 10.0, a 10.0.1, a 10.0.2, and a 10.0.3. That all summarizes into this. Now, the cloud has these subnets. How many routes do I need to send to the cloud for this environment? One. Because once the cloud if the cloud knows to reach 10.x, go to the data center, the routers in the data center know how to reach everything. But we only need to send a single route to the cloud. Now, what if our data center had all these subnets? What if it had, just out of argument's sake, let's say we've got these subnets, let's add some more subnets. Let's add a 10.0.4.0/24. This is going to get ugly. But anyway, maybe I don't want to do this. Maybe it's going to make it ugly. But let's say I wanted to add 10 more. Let's say I wanted to add the 10.0.4.0, 10.0.5.0, 10.0.89.0, 10.0.99.0, 10.1.3.0, 10.2. Or 10.2.3.0, 10.3.3.0, 10.4.3.0. I could still send a /10 route. In fact, I could send a 10/8 over here if I chose to the cloud. If I really wanted to, I could send that to the cloud. And then I could basically have 254 subnets here. I could have 254 subnets here. And I could have a bunch of subnets here. So you see where I'm coming from? By addressing our addresses right, we only need to send a single route or a summary route. And then we can do some traffic engineering and determine where our traffic is going to go and when it's going to go there. So these are kind of those things that we're trying to do and why we're trying to do it. So let me try and see if I can show you a little bit more of what we're trying to subnet here. These things don't exactly completely come across perfectly. We're trying to show them on YouTube. Most of our content is really made for Zoom. Because but when we try and do stuff for the community, we try and do some stuff on YouTube for it. And the reason we choose YouTube versus Zoom is this way people can go back and see the recordings later. So we want to really give the community a chance to be successful. So that's what's going on here. We can change this. So now let's go play with it and let's go start thinking about how we would design the system. But I'm going to say it one more time. For logical router addresses, we use a /32. For WAN links, we use a /20. We use a /30. For LAN links, so WAN link /30. Loopback addresses on router /32. For LAN links, we use /24, but we can go as big as the /23, and that's about as big as a subnet we're ever going to get due to broadcast. So I'm going to do this. We're going to get into some architectural design with systems. We're going to talk about laying out your systems, and we're going to talk about optimizing the routing. So we're going to get into the good stuff real soon. But I want to make sure we address questions. Chris from my team is going to aggregate questions. So let's make sure we do them first. Pierre, do I always make sure to give a network prefix that is different in your LAN than the one from the cloud? Pierre, we're going to get to that soon, but I always choose a different Cider block for my LAN or my data center than I would for the cloud, and I always choose different Cider blocks per cloud. And I'm going to walk you through that so you can see exactly how and why. Great question, by the way. Are there others, Chris?
No, that one was there before you asked for questions. So.
Okay. So let's see if anyone else has any other questions. And if so, we will answer them. And if not, we're going to move over to the fun part, the architectural part, the design part.
Yeah, this would be a good time for me to find out if the Jeopardy theme song is public domain or if it's or if I have to pay for it.
That sounds good. I always do.
Yeah, with our 10-second delay.
That's really a great idea. So let's see if anybody has any questions. And if not, what we're going to do is we're going to go have a party and we're going to do some network architectural designs. First, we'll do it from an IP addressing scheme. And then if you guys want, we'll add some BGP because, there's me, there's BGP. I've got 10,000 hours of BGP. I literally traveled the globe consulting on BGP and PIN multicast and multi-protocol BGP. So love talking about BGP. So we want to talk about some BGP and some traffic engineering after we go through the addresses and you guys are all having fun and you just say BGP, we'll do some BGP. So AWS BGP, Cisco BGP, it's all everywhere. Love talking about networking. Networking is the plumbing. So it doesn't look like I see any more questions. It looks like everything is doing great. I appreciate the nah. So Tom, I know you got it. So Eferistopoli, and we'll keep moving forward. So now, let's start getting into the architectural design, which is one of my favorite components. So let's now think about this. Now let's talk about why I'm really big on these things. So let's go in here. We're going to come up with a new slide. I'll share my desktop. So let's work over here. So now let's say, and then we're going to talk about how we can really make this great. So let's begin. Let's say we've got a data center here. And data centers are here to stay, even though the cloud is here to stay as well. So now let's say we've got our data center. Now, when it comes to real cloud architectures outside of solution architect certification exams, what we actually do in the real world, we're dealing with multiple clouds. Now, typically speaking, to let you know how prevalent multiple clouds are, a year ago, 29% of all people were on a single cloud provider. Right now, 3% of organizations that use a cloud are on a single cloud provider, and everybody else is multi-home to multiple clouds. So there is no such thing as a single cloud provider anymore. That's why we teach multi-cloud architecture. That's why we've taught multi-cloud architecture forever. And the reality is a single cloud is a single point of failure. So it's just bad architectural design in general. So we're always going to be talking about multiple clouds, and that's the reality of our lives. So now let's look at it this way. Let's look at exactly how elegant we can get with our addressing and why we're going to do it. So let's say this were AWS. And let's say this was Azure. It could be GCP, it could be Oracle, it doesn't matter. I'm just picking AWS and Azure. You figure that's got to be what, 85, 90% of the market share. So now let's look at this over here and let's really make this elegant. If Azure is using this block, 172.16.0.0/16, and that's your main Cider block, and you've got 100 subnets in there, who cares? And in AWS, you're using the 172.17.0.0/16, and you're using over here 10.0.0.0/16. and you're connected, and you've got a direct connection to AWS, you've got a direct connection to Azure, you've got a VPN backup to AWS, you've got a VPN backup to Azure, you've got a private line or two, direct connection, express connect, whatever you want to call it. It's the same concept between Azure and AWS. Now, do you have high availability connectivity in this situation? So we're going to evaluate the network from a couple perspectives. Well, can you reach AWS? Yes. If the direct connection goes away, can you reach AWS? Yes. If the direct connection and VPN connection goes away, can you reach AWS? Yes. You can go through the Azure direct connection, or you can go through the Azure VPN. If the Azure direct connection goes, you still have got a VPN. So you've got a highly redundant environment in this. So from networking right now, this already checks all the boxes of a high availability system. No single points of failure. Now, inside of here, let's see what network addresses need to be seen by whom. AWS and this cloud only needs to send a single route. And the only route that AWS needs to send to any of its neighbors is this. That's the only route that it's going to need to send, is this specific subnet. It's going to have to send that route to Azure, and it's also going to have to send that route to the data center. And we must know it on both sides. I don't know what happened there. Bear with me. Bear with me. We'll get this straightened out. I think I bumped a button somewhere along the line. Bear with me a second. We'll clean this up for you a little bit so I can make it look as good as we potentially can. Okay, so there should go. That should work. Okay, so nope, still too big. There's got to be better software for that we'll figure out for sharing files in real time. But okay, so what we're talking about over here is AWS needs to send this route both to Azure, and we also need to know about it in our data center. Now, what will happen is these routes are going to be sent via BGP. So if Azure tells the data center about it and AWS tells the data center about it, BGP will ultimately look in its routing table, and it's going to prefer the path with the highest weight, prefer the path with the highest local preference, prefer the one with the shortest AS path. And to reach AWS, this link will always be preferred, and this link will be a backup. Now, at the same time, Azure is going to need to send routes too. Azure is going to need to send two routes to two places. Azure is going to, and I don't know why this thing keeps happening every time I do some cutting and pasting. Azure is going to need to send this route. It's going to have to send it to AWS, or otherwise AWS won't know how to reach it. And it's also going to have to send it to us in the data center. So what do we need to know in terms of how to do this?
Hey, Mike, just share the PowerPoint window in StreamYard, and I'll take care of it.
Okay, sounds good. So. Oh, okay. Never mind.
Yeah, it's sharing the window, the whole window.
Okay, perfect. Okay, so are you moving stuff around, or was that me from before? Okay, so while we're here, I'm assuming everybody can see my screen. What we're going to do is as follows. Note the number of routes that we're sending and where we're sending them. So we're sending this route to the data center. And then what routes does the data center need to tell? The data center needs to tell AWS and Azure about its routes. And what are its routes? I'm going to tell you right now. I'm going to send the 10.0.0/16. It's going to send it to two places. It's going to send it to AWS, and then it's going to send it to Azure. Now, how many routes do we really have floating around our wide area network here? When we really think about it, this route, and this route. So there's only 3 routes in the routing tables that are being sent from 3 clouds. Only 3 routes, just 3 of them. Now, it doesn't matter how many subnets we have in here. How many hosts do we have in the /16? 65,000. How many hosts do we have here in the /16? 65,000. How many hosts do we have here? 65,000. How many subnets can we put in these ranges? A whole lot. A whole lot. So Azure is going to have to send the 172.16 to AWS, for example, and AWS is going to have to send the 172.17 to Azure, and Azure is going to have to send the 172.16 to AWS, and AWS is going to send the 172.17 to the data center. Our data centers are going to be sending the 10.0.0/16 to AWS and Azure. And then in the end, what we're going to get is 3 routes. 3 routes. 3 routes. Now, why could we do 3 routes? Because this Cider block is discrete, and this Cider block is discrete, and this Cider block is discrete. Now, if this was all in the 10.0.0 space, and this was all in the 10.0 space, now, could this still work? Well, if we change the subnets. Well, the answer is possibly yes, and probably. So, for example, if the subnets that we were really using in this block, I'm going to make it up on the fly, so bear with me if my mental math is wrong, because I'm thinking about it and logically doing it. But if what we did over here included these subnets, 10.0.1.0, and this was, let's not do that. And then this was 10.0.2.0, and this was 10.0.3.0, and these are all /24s. And then over here, /24, /24, /24. Now we did the same thing over here, but now we had 10.0.4.0, and then we had 10.0.5.0/24, 10.0.6.0/24, 10.0.7.0/24. Now, on the surface, this is going to look really good, but I'm going to show you why it's going to break and be a disaster, which nobody thought of in a minute. So now we'll go over here, and because this is a good addressing plan with no thought, but mathematically, this is a good routing and switching subnetting plan. But I'll show you where this is going to break. So let's go over here. So now we've got 8, 9, 10, and 11. Let's do this real quick. Let's go back over here. Now we go back over here. Let's get rid of this. Let's get rid of this because it's getting too busy. It won't make any sense. Let's get rid of this. 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 Now, oops, I think I just deleted something we needed. Let's just not get rid of that 172.16 because every time I try and delete that, it seems to delete other things. So right now, this will work. Does everybody see how that even though we were all in the same CIDR range, our addressing will still work? Because it will. Our addressing will still work in this particular environment. And it's going to work great because we don't have any overlapping IP addresses, so it's going to work. Now, where things are going to get ugly, though, with regards to it working are as follows. What happens if we need an additional subnet over here? We've used contiguous ones over here, 0 through 3. Now this one has 4 to 7, and now this has 8 to 11. Where do we add the dot 4? Oh, wait, we can't. So where's our next subnet going to start if we need a new one? We're going to have to find something unique, like 10.0.12.0/24. And then if we need a new one, what are we going to do? 10.0.13.0/24? And then what's going to go on over here? Oh, wait, we need a new one. This is now going to be 10.0.14.24. And now we're going to go over here and we're going to get into this ugly range of 10.0.15.24.0/24. Now you can see how rapidly this gets big and ugly, as you can see that. So that's why we need to think it out. So that's why if you're using private IP addresses for your subnets or your VPCs, and you're going to be using private addresses anyway, pick an addressing plan that's going to give you room to grow. Maybe the 10 address space, maybe the 172.16 for one VPC, maybe the 172.17 for another VPC, maybe the 172.18 for another VPC. The point is make it so you can just send one route to your people. And by sending just a single route to your people, here's what we ultimately do. We create an environment where we need less routes in the routing table. Less routes in the routing table means less memory in the routers. It means more simplicity, more elegance, and the ability to traffic engineer. So now that we've got the fundamentals, which we've just talked about, which is the subnet and the supernet, and we've talked about ways to spread your addresses out. And by spreading our addresses out delicately in a manner, we put ourselves in a position that we can design it. So before we optimize the routing, and we're going to get into some fun routing things, I want all of you to optimize and design a system. We're going to do it real time. I'm going to ask you the questions. I'm just going to be Mike, the CEO, instead of Mike, the network architect. All those years of working for Cisco and training engineers at Cisco and Riverstone and WorldCom, which is now Verizon. We're going to do it. You guys are going to teach me because I know you guys are all network architects, cloud architects, and experts. And what's the point of doing all this training? We're not based on certification. We're based on getting cloud hired. Big difference. Anybody can get you certified. We get you cloud hired. So let's get you cloud hired. And accordingly, let's do some architecture work because we're cloud architects. What do cloud architects do? Architecture work. So let's do some architecture work. Now let's play with the network. So let's have some fun here. Okay, so now we got a new slide. We're going to deal with a whole bunch of clouds. Let's say we're going to deal with AWS. Let's say we're going to deal with Azure. All right, let's deal with GCP. Okay, so now, because we're real and this is practicality, this is the data center. All my students are become knowledgeable on how to build private clouds because organizations use them. So let's say the data center is running an OpenStack cloud. Everybody runs an OpenStack cloud. American Express runs an OpenStack cloud. American Airline runs an OpenStack cloud. You name it. Verizon runs an OpenStack cloud. IBM runs an OpenStack cloud. Lots of organizations use an OpenStack cloud. Now we've got 4 organizations. Your task, should you be able to complete the mission, is to make sure that only one route is sent between every one of these VPCs. We would like to assume that each cloud could get as many as 25 to 30,000 servers, and we want to allow room for growth. So assume we have 30,000 or more servers, but no more than 65,000 that is going to be in an AWS. So say 40,000 in AWS, 40,000 in Azure, 40,000 in GCP, and you're going to use subnets that are going to give you less than 500 hosts per subnet. But you might have to put 35,000 people to 40,000 people in AWS, 40,000 servers in Azure, and 40,000 servers in Google. And you know what? In our data center, you know what? We also have 40,000 servers. So I need you to get scalable. I only want to see 4 routes in the routing table. 1 route from AWS, 1 route from Azure, 1 route in Google, and 1 route for the data center. Somebody pick an addressing scheme. We've got a Class A, Class B, Class C addresses we can use. We've got, let's use RFC 1918 private addresses. So what are those addresses, RFC 1918? Well, we've got the 10.0.0/8. We've got the 172.16 all the way to 172.31/16, and we've got the 192.168/16. So somebody out there, come out there and tell me how to make my addresses. Because when you do this, that's when we're going to build on this. Abigail Marks, give me a something we're going to use for the data center. Pierre, okay, the 10.2.0.0/16. It's an odd one to start with. So Pierre, are you doing a 10? So if you want to use that for the data center, and we could use that because it could potentially be a very good one, Pierre, what would you then use for Azure, GCP, and AWS? Because maybe I missed one for you there. Because Pierre, your 10.2 is a perfect subnet to use. I just want to see what your logic is. Because we can totally use it. All right, if I have to lead it, I'll lead it. Can anybody think of anything? Tell you what I would do. I'd work with Pierre's suggestions, but just tune it a little bit. I would make the data center, or what we do, I would make it a 10.0.0/16. What I would do. Then when I go to AWS, I go to 10.0.0, I go to 10.1.0.0/16. You know what I would do at Azure? No worries, Abigail. At Azure, I would make this a 10.2. And over here, for Google, I would make this a 10.3. I said we needed the ability to have at least 30,000 servers. How many servers, or could I potentially have in an environment where I have a /16 submask? 2 to the 16th minus 2. Somebody with a scientific calculator, 2 to the 16th. Or better yet, do it in your head. 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, 2048, 4096, etc. Okay, there you go. Asim, better yet, you did it with the math, smarter than me. 65534. Great job, Asim. So that's really what I was trying to impress upon you. Each one of your environments gives you 65,000 plus addresses. Amarath, great job. And using the calculator is probably smarter than using your fingers like me. But I do lots of stuff in my head. So, or gut. Exactly. With AWS, we've got 65,000. With 65,000 with Azure, 65,000 with Google, and 65,000 in our data center. Do we have room to grow? Is that enough, everybody? 4 routes. Nice and simple and elegant. It's going to work really well. Amelia, hola, ¿cómo está? As well. So, these are great things, and we're thrilled to talk about it, and that's why we do it. That's why it's elegant. Put your things on boundaries. Now, let's take this and let's make it look a little bit nicer. Now let's think about how, now that we know what can we do, how do we tune it? How do we engineer it, and how do we make it work? Actually, no, Caroline. If it was a /8, it would be 10, and then it would be 11, and then it would be 12, and then it would be 13, and then it would be 14. That's where the boundary would go. So /8s are things go from 10 to 11. A /16, here's the place where we've been manipulating. We've been manipulating the second octet. The /24, we've been manipulating the third octet. So no, Caroline, it's actually going to be that we actually have it correct here. But really do appreciate the sanity check, and trust me, I make enough math errors that the sanity check is always a good thing to have. So now let's look about why we're being careful with this. So now we're talking about addressing, and because of this, we have clean routing. We know to reach AWS, go here. To reach 10.1, go to AWS. We know to reach 10.2, go to Azure, and we know to reach 10.3, go to Google. And we also know in the data center, reach 10.x. And now we're in the place, everything's classless IPs, everything's smooth and running clean. Now let's look at the traffic engineering. Now we've talked so far today, and as we're talking today, we're talking about the subnet masks. So as we're talking about subnet mask lengths, and as we're talking about these kind of environments, now let's think about what we're talking about. How far is the subnet mask? So routers look at subnet masks. The longer the subnet mask, the greater the specificity of your routing information. So let's get a little bit into routing, because I want this to be a really good experience for you. And I want to tie it back to things that matter for you. So look at it this way. If I give you this subnet, and I give you this subnet, okay, 192.168.0.0/16. This is a big address block. Does everybody see that if I take this address and I subnet it down, I can get a 192.168.1.0/24 and a 192.168.2.0/24 and a 192.168.3.0/24 and a 192.168.4.0, et cetera, pulled out of the /16. We've been doing this today, but is that abundantly clear to everybody? If that's abundantly clear to everybody, type cloud hired in the box, so I know you're here, because this is really important before we dive deeper. I want to make sure you get that. I want to make sure that you understand that all these things, let me know what the cloud hired and get it, as a subset. Exactly, a subset. Exactly what's going on. So now, if I gave you let's pretend you're a router today. Instead of being a person, you're now a router. I'm a router. Chris is a router. Daniel's a router. Mark's a router. Pierre's a router. Tom's a router. We're all routers today. Now, if I gave you the information 192.168.1.0/24, and I also gave you a route 192.168.0.0/16, which is more specific? Which points you to something where you know exactly what it is? Do you know, for example, 192.168.1.0, does that identify it very specifically to the /24, these 254 hosts, where this 192.168.0.0/16 could be any of 65,000 plus hosts? Is it clear to everybody that it's more specific to 192.168.1.0? So the longer your subnet mask is, the more descriptive your information is. So by comparison, one of these days I'm going to learn how to use Windows, or else I'm going to go back to a Mac. So now that we go over here, and if we go back to this 192.168.1.24, now which is more specific, 192.168.1.0/28 or 192.168.1.0/30? So let's say you're a router, and let's say let me start with the /16 on the top so I don't drive everybody batty with the way it appears. So we should be working around at least the logical order. So now going here, everyone, what is the most specific, which gets you knowing what the subnet is within 1 or 2 host bits? The /30, Ogrendra, great. Caroline, exactly. So it's most specific because it is most descriptive. Now, if I tell you explicit information, are you more likely to believe it than if I give you more general information? What if I said to you, my cat Cindy weighs 3.1 kilos and she eats 1,427 kilocalories per day? Is that very specific about her weight and her dietary intake? Or what if I said, my cat Cindy weighs between 5 and 10 pounds and she eats a lot? Which is more specific? Giving you an exact weight and a number of kilocalories or kilojoules of energy? Or just saying, hey, my furry cat, eats a lot? So the better your access to information, the better decisions you can make. So what routers do is they look for the most authoritative information. And what is the most authoritative information? The most specific. My cat Cindy weighs 3.14159 kilos, which happens to be pi to a certain number of digits. It's very specific, other than my cat Cindy weighs a lot today. So routers take the most specific. So this is your secret for everything. This is your secret for traffic engineering. This is your secret for high availability. This is your secret for everything. So specificity of information. So now let's deal with common environments. You've got a data center. Happy data center. I love data centers. I've been building them for 30 years, almost 30 years. I love data center because I love the cloud. The cloud's another data center, that's all. Let's say this is AWS. Okay, we're going to connect to AWS. Okay, let's do some architectural work. I need to connect to AWS. I run latency sensitive applications where I need my latency to be consistently less than 2 milliseconds, and I need at least 8 gigabits of throughput per second. Okay, what kind of connection do I want here, everybody? Do I want a VPN or do I want a private line or a direct connection, and why? Somebody tell me in the chat box. Asim, I do need a direct connection. Alex, I do need a direct connection. And the reason I need a direct connection, everyone, as I just told you, I need consistent latency and I need consistent bandwidth. So it has to be that, because internet traffic is best effort. When traffic goes through the internet, we don't know what's going to go, and our latency is going to be all over the place. And we're going to have variations in latency, and that's called jitter, which is never, ever, ever a good thing. So that's there. So now, as all of us understand these things, now let's say what happens if you have 2 direct connections. When you use a direct connection with AWS, do you use static routes or do you use dynamic routing? With a VPN, you can choose either. But with a direct connection, which is what pretty much every major company is going to need, or multiple direct connections, what's going to happen is they're going to need some consistency. And when you use a direct connection, you're going to have to use Mike's favorite routing protocol, BGP. So BGP. So when we're dealing with BGP is going to help us determine the path through the system. So now, if you've got, let's say you need a 10 gig low latency primary connection. If you need low latency for your applications, you're not going to get away with a VPN backup. So you're going to have a direct connection and a direct connection backup. Now, here's where things go wrong. And here's where you need to know routing. And if you know routing, you can make the simplest, most elegant, beautiful solutions in the world. And if you don't know routing here, everything will fall apart. So let's think about it this way. Does anybody understand what's going to happen here? Now, when you buy high availability connections, you always buy them across two service providers. Always. You would never, in good architectural design, buy two links or two pipes or two connections from the same service provider if you had a choice. Because if I buy them all through Verizon, and Verizon is an incredibly good service provider, if I buy them all through NTT, another incredibly good service provider, or if I buy them all through AT&T, another good service provider, or CenturyLink, it doesn't matter. All service providers have outages. Every last one of them has outages. So we buy one link on, say, Verizon, and another link on AT&T or NTT. We always buy across two links. Now, can anybody think about the challenges of buying links from two phone companies? One link is 1 millisecond, somebody else's link is 2 milliseconds. And that, just that, will cause all kinds of problems if we're not careful. So if we were to get two direct connections to the cloud, and we do nothing, and the cloud is, this is their CIDR range, 10.0.0.0/16/16, and let's say, for example, the company has a 10.0.0/24, and they have a 10.1, let's make sure I got this right, 0.1.0/24. Okay, so actually, so let's say these are the two addresses that we've used. Yeah, okay, let's say we're using these two subnets. Now, right now, if we set up BGP and do nothing, these three subnets are going to be sent on the top link and on the bottom link. And they're going to look identical on both sides of this equation. And when the router is looking at the traffic, and when we deal with BGP, we have to send our routes in both directions. I'm going to make this just one direction to make it look simple for you guys. So right over here, now the router is receiving this routing information on the bottom link and this routing information on the top link. Does anybody see a challenge here? How does the router know which links to take? Routes are the same, they're equal cost. So now in the routing table, we've got two equal cost routes. Now, when we're dealing with BGP, there's always an algorithm, and there's always a thing, and there's a reason we're not going to use a link aggregation group here, because we bundled two links across two different service providers that have two different latencies. We have a problem. So if we're going to use a link aggregation group B3 collector, we might have three links in a link aggregation group through Verizon, and then we're going to have a backup link aggregation group through, say, AT&T. And we're going to bundle all the AT&T links together and all the Verizon links together. But if we're only going to deal with, say, a 10 gig link to the cloud direct connection and a 10 gig backup connection, then if that's going to be enough, we're going to have this. Now what we have is we've got two sets of equal cost routes. So what will ultimately happen is we may be sending data to the cloud on this link through AT&T, and then half of our traffic could be coming back through AT&T and half of it could be coming back through Verizon. So what happens is packets get out of order. Some arrive on time, some arrive later, because AT&T might be faster than Verizon. So if AT&T is 1 millisecond and Verizon is 2 milliseconds, which is in the realm of tolerance, what can happen is you can get your packets twice as fast through Verizon than AT&T, and you get them out of order. So whenever you're dealing with multiple connections to the internet or multiple connections to your cloud provider, you really need to do something about it. So you've got two options. Option one is, which is basically what they teach at the AWS Advanced Networking level, which is like intro to networking. They say just block this. Now, the reality is, in 25 years of networking, I haven't met many people that thought it would be cool to buy a $10,000 to $100,000 connection per month and just block it for the heck of it. My customers don't tell me that. My customers want to use their backup. So, given that that's the reality, and, the AWS Advanced Networking is so basic, it wouldn't meet the needs of any customer. We need to do things that are more CCIE-like to make better use of the system for our customer. So what an organization would do is they're going to load share across these. Now, how do we do that? Well, there's a lot of ways we can do it. But now look at this very carefully. For right now, let's just send this subnet on the top, the 10.0.0.0/24. And now on the bottom, let's send the 10.0.1.0 subnet. Now, the routers sitting at the data center have two routes in the routing table. And they say, hey, wait, to reach the servers in the 10.0.0 subnet, take the top link. And then they say to reach the 10.0.1.0 subnet, take the bottom link. Does that make sense to everybody right now? If you know to hit the 10.0.1 subnet on the bottom link, take it that way. And the 10.0.0 on the top link, take the top link. Does this make sense to everybody? Let me know with the cloud hired if you get it. If you don't get it, let me know. And then what we'll do is we'll answer some questions. Alex, we temporarily have a single point of failure, but we're going to have to fix that. We are creating a problem along the way with our fix. But everybody sees this. Okay, so Mark, you got it. B3 collector. Pierre, you got it. So right now, what we're doing, Pierre here, and Marla here, let's go through this one more time. Routers always take the most specific route. Most specific route. So if on the top, I send a specific route to this router that's going to be, say, sitting over here, and this router over here is going to have a routing table. And in its routing table, the router is going to say, hey, to reach 10.1, go out this link. To reach 10.0, go out this link. So the routers are building a map. Where does this information come from? It's going to be put into BGP. And BGP is a routing protocol which tells everybody how to reach their subnets. So if we do this right now, and, what's his name actually caught it very perfectly, Alex Wood. Right now, the top link only is only the servers of the 10.0.0/24 subnet are reachable via the top link. And the servers on the 10.0.1.0 subnet are reachable on the bottom link and the bottom link only. So if this link goes away, will anybody be able to reach the 10.0.1.0 subnet? The answer is no. And if this link were to go away as it stands right now, this link, because that's where the BGP routing is, no one will be able to reach the 10.0.1.0 subnet. So does anybody think this is a good situation right now? I don't. We've got a problem. So here's what we have to do. Amrath, you are correct. This is not a good situation. And Yogendra, what happens if the connection is down? BGP is not going to switch at all. Right now, we have a major problem. But we also solved a major problem. Right now, what we solved is we've load shared 50%. 50% of the traffic is going on the top link. 50% of the traffic is going on the bottom link. And we don't have any out of order packets because we've told the link switches to go. But we do have a problem. What happens if this link goes away or this link goes away? Half of our subnets are not reachable. So now let's send a summary route or a non-specific or a non-preferred route on both the top link and bottom link. We're going to put it into BGP and we're going to tell BGP to tell the world about it. So by doing it this way, by telling BGP to tell the world about it, that changes everything. So now let's put this summary route 10.0.0.0/16 on the top. Now, guess what? Let's send that summary route on the bottom. Okay, now everyone, what is the best path to reach 10.0.0.0/24? Top link or bottom link? 10.0.0.20.0/24. pop that link, pop the answer top or bottom into the chat box. We're going to go on the top specific link. Exactly. Things working perfectly. Now, everybody tell me. Let's make sure you guys all get this first. Exactly, because the top is the most specific. Pierre, you got it. Noel, you got it. B3 Collector, you guys are doing great. Fantastic. Now, before we get into the failovers and the high availability part, and oh wait, Pierre, you're right. The /16 is going to be ignored because it is not specific. But the secret lies in that /16 for redundancy purpose. Carl Kenya, excellent. Hey, Carl Kenya, you're now dealing with BGP concepts, which most CCNAs don't even know. And this stuff doesn't even come into play to the CCNP/CCIE level. So Carl Kenya, great job. Nice. Now, which link is going to be used to reach 10.0.1.0? The specific link for 10.0.1.0, is that going to be at the top or is that going to be on the bottom? Bottom. Bottom, exactly. So the bottom is going to be used. Now, I have a feeling you guys got it. I have the feeling that you guys are really getting stuff that's kind of pretty cool. Excitement's building. So now, let's say this top link completely goes away. It's gone. The link is gone. It's all dead. There's no more link. Now, how are all these subnets reachable? Is there any way to get to AWS for the 10.0.0.0/24 subnet? Is there anything? Are there any routes that would say, hey, I have a path to 10.0.0/24. It might not be the most specific path, but I still have something that tells you I know how to get there. Yogendra, exactly. It's part of the /16. Pierre, exactly. So here's what happens. The data center now knows, hey, I can reach anything in the 10.0.0/16 space. You go over here. So what happens is, by using a more specific route, we can traffic engineer our path. But by having that summary or aggregate route, if the more specific path goes away, guess what? We've got a backup path and we're still good. So this is why we're doing this. You guys are doing fantastic. I'm really proud of you. I'm really excited. You guys are really, really doing great. So let's keep at it. You guys are doing great. So now, let's pretending we're talking about BGP. So BGP has a decision algorithm. Every one of you, I want you to look it up right now. I want you to go look up the BGP algorithm because I'm going to ask you to use it. So as we go through this together, so it's going to be the BGP decision process. I'll give you a link. BGP decision process. I'll give you a link so you can all see it. Sounds good. So let's go find something from the Cisco web page. How does BGP select the best path? Well, actually, let's make sure this is accurate because I see it on the internet. Let's make sure if the next hop, don't consider it. Prefer the path, that's true if the routes are the same. Okay, so this is a very good example of the BGP decision process. I want you to all look at it. So here's, when we're dealing with BGP, there's a bunch of attributes. And if you guys want to learn about BGP, I've done lots of BGP videos, lots of BGP demos, and there's plenty of information on that. And if you guys want, we'll probably do it. But let's just say, let's play with BGP very quickly for a few minutes. So in this particular environment, and in this exact particular environment, let's talk about it. So let's say you've got multiple routes. So let's say we've got multiple links. What is the first attribute. If the next hop is not available, don't put it in the routing table. That's going to get pretty complicated discussion of interior gateway protocols, exterior gateway protocols, and everywhere in between. Ernest, we're thrilled to have you. And Ernest, honestly, you can always go back and watch the replay if you're having fun. So please, we're thrilled to have you. So here's what we're dealing with. So in this particular environment, let's make sure we're going to learn our routes from AWS the same way. Let's say we've got two direct connections. And let's say we want to use, let's say the top one is AT&T. Let's label our WAN connections. On the top one, we'll call it ATT. And on the bottom, while we're at it, we'll call it NTT. Nippon Telecom is a very good global internet service provider, WAN provider. So we'll say ATT and NTT because they've got similar things. So, okay, we got an American phone company and a Japanese phone company. Okay, so now we're dealing with this. Now, let's say we're talking about the subnet 10.1, this particular subnet. And let's say we're going to send this subnet on both links. But let's say on the top link, we change the weight of this route to 35555. And on the bottom link, the route is in BGP listed. Let's just make sure we pop this on. Okay, so this is the weight attribute that we've tuned. So the routers, let's assume the router receives the information. It's got this route with a weight of 35,555. And on this link, the router sees the route, and the route has a weight of 32768. So which route does the router send its traffic, on the top link or the bottom link? Well, let's look at that BGP decision algorithm that I sent you. If the next hop isn't available, don't put it in the routing table. If the path is good, prefer the path with the largest weight. So everybody, which link am I going to be taking? The top link or the bottom link? And why? Yogendra, the top link. Why the top link? Somebody tell me why Asim, the top link, exactly. Why the top link? It prefers the largest weight. Okay, good. So now I'm going to change the top link to 10,000. A bottom link will be used because we're going to choose the path with the largest weight. Okay, now, guess what? After weight, what do we choose? The largest local preference. So, what's next? We're going to take the route. We're going to pick the one with the largest local preference. So now let's say we've got 200 on the top link, 100 on the bottom link. Let's switch them around. 200 on the bottom link, 100 on the top link. Which path are we going to take? Somebody tell me, which path are we going to take for this route? The bottom link, exactly. Okay, so now let's play with it. Let's do some cool traffic engineering. Now let's load share. So you guys got it. We played with the weight. We played with the local preference. And don't worry, we're going to play with the autonomous system path. We're always going to have some fun here. This is the best routing protocol in the world, and it's really, it's terrific. So let's look at this. So now let's get a little more complicated. So now let's put two subnets, and let's do some load sharing. On the top link, we're going to put 10.0.0.0/24 with a weight of 200. And on the bottom link, we're going to keep this with a weight of 200. And then we're going to add a 10.0.0.0/24 with a weight of 100. Okay, now, which link is being used for the 10.0.0/24 subnet, and which link is going to be used for the 10.0.1 subnet? So right now, we should be using both links. The question is which link we're going to use for which subnet. I want you guys to tell me in the window below. Nice job there, Pierre. Nice job there, Caroline. Woohoo, this is well above CCNP level networking you guys are doing. So how is it now, Caroline, you're my student, Pierre, am I my student? So how is it we ramped up so fast? Because we worked really solid on the fundamentals. And when the fundamentals are strong and you get the fundamentals, we can escalate really quick. It's really hard to go when you don't have the fundamentals. You're missing the numbers in there, but I kind of think I know what you mean. So there's that. So, okay, good. So now let's play with it a little more. So if by comparison, and some of these things are going to get a little goofy, like the origin code. For those of you in the cloud computing world, you're probably not going to be redistributing and calculating your IGP and AGP and mapping it. So let's play with things that you're going to be more likely ready to tune. What are you going to be really likely to tune? The thing that you're going to be really likely to tune is as follows, is the autonomous system path. Okay, so here's what happens. I'm going to map this out for you, and then we're going to go back to this again because I want you guys to get this. Because honestly, just knowledge of BGP is one of the most critical things you can know in cloud computing. So the way the internet works is it looks like this. There's going to be an AS1, and there's going to be an AS2. And let's say we've got an AS3. And maybe we have an AS4. So what happens, the way the internet is structured, you've got a whole bunch of organizations. And each one of these organizations is going to be called an autonomous system. And what happens is each internet service provider is going to have connections to other service providers. And there's not going to be a rhyme or a reason for the pattern. It's going to look like something like this. These guys are connected to these guys who are then connected to these guys who are then connected to these guys. And I use the term guys loosely, just in reference for a service provider. So here's what will happen. Let's say you've got this subnet over here. 1.1.1.1. And Noah, Pierre, an autonomous system means something other than under the control of an organization. So AWS would be an autonomous system. Google would be an autonomous system. It's basically just an organization. Now, AWS is probably several autonomous systems, but we're really talking about a company. So what'll happen is if 1.1.1.1 is sitting on AS5, and you're in the position of AS6 over here, and you do on the router, you do a show IP route 1.1.1.0/24. Here's what you're going to find on your router. You're going to get a route to it, and it's going to tell you to go here. But what you're going to see in the routing table is it's going to look like this. It's going to show the route, and the route's going to look like 1.1.1.0. What you're typically going to see is a B in front of it to say that it's coming from BGP, and then you'll always have a mask, and the mask will be in /Cider notation. This is what you're going to see on the routing table, and you're also going to see these attributes, at least from the BGP. If you do a show IP BGP, you'll see A5, then you'll see A4, then you'll see A3, then you'll see A2, and then you'll see A1, and then you'll see if you're sitting on over here on this route, and this is what the routing table you're going to look at. If you're here and you're looking for the route for here, notice what you see. You see the route, you see the prefix. You'll also see the weight, whatever it is. So let's say the weight is 32768, and let's say the local preference is 100 because it's the default. And you're going to see all the autonomous systems that your traffic passed through. So it's going to show you all the different internet service providers your traffic passes through. So now I want you to think about this. Let's pretend now there's 2 links on your AS6. You could learn the route via 2 ways. You can learn it via here, like we just showed you, this link to this link to this link to this link to this link, back to this link. You could learn it that way. Or you could learn the same route directly from A5 to A6. So if you're looking in your BGP table on a router, you're going to see this. You're going to have these 2. This is what's going to be in the routing information base on your router. You're going to be learning the route via this path, and you're going to be learning the route via this path. So now let's look pretty carefully at this route. The prefix length is the same. They're both /24, so one's not more specific than the other. The weight is identical. So we're not right from the weight. We don't know whether we want to go this way or this way. Then we'll look at the local preference. The local preference is the same, so we're not going to go this way or this way. Then we're going to look at the AS path. Which AS path is shorter? One AS hop going straight to AS5, or going through AS5, AS4, AS3, AS2, and AS1. Which one looks like a more direct path? Go straight from A6 to A5, or go from A6 to A1 to A2 to A3 to A4 to A5. Clearly, it's a shorter AS path to go straight there, Caroline, exactly. Go straight from A6 to A5 because it's got a shorter autonomous system path. It's a single internet service provider versus 1, 2, 3, 4, 5. So shorter, less internet service providers, most likely better. Now, if all these things were 100 terabit connections, and this thing from here to here was a 100 megabit connection, it might be better to take the longer path. But we can tune it, and we can know when we understand it, but we've got to do the routing. So now let's go back over to here. Now the next thing we're going to talk about is something called AS path prepending. Now this basically means we manipulate the path that the route has been come through. So previously, when we go back to this slide, when we learn about the route here, we've learned about it because it's traversed all these autonomous system paths, which is really, really great, which is really exactly what we're trying to do. But what if we just wanted to tune it? So now let's instead of playing the weight, let's call this autonomous system 1 over here, AS1. The reason we're going to call it AS1 is there's not going to be a lot of numbers we have to play with, so it's going to look prettier. So let's call this AS1. On the top link, the 10.24, we want that to take the top link. Do you know what the route's going to say on it? It's going to say AS1. Why is it going to say AS1? Because we traversed AS1 to get there, and that's what it should be. And now let's do the bottom. Let's say we want the 10.0.1.0 preferred on the bottom. We're going to leave that by default as AS1. Now on this top link, can we make that second route look ugly? What if we did AS1, and what if we prepended or added an autonomous system? We manually typed AS1 again. So when BGP learns the route, we learn AS1 for the top or AS1 twice. Now that is us manually prepending or adding to the path an additional autonomous system to make the route look ugly. Now on the bottom, what we would do is we would prepend the next one for the next subnet. And by the time we do this, look what happens. Can you eyes all see that this is now the shorter path for the top? And this is now the shorter path for the bottom. But this becomes the backup path, and this becomes the backup path. So prepending autonomous systems is part of the BGP RFC. So we're allowed to do this. This gives us a place for manipulation. So the answer to that is yes. And that's why it doesn't break anything. BGP's been designed for this. These are in networking, we call them the nerd knobs. And we're the nerds that know how to leverage the nerd knobs to basically say, need a little more traffic going out this way. Tune this, go that way. Tune this, go this way. So This protocol was used for this kind of scalability, tunability. Because BGP was designed for this scalability and tunability, it's used to connect to external entities. So by connecting to external entities, let's look at when we connect to AWS, they're not our company. So we don't want to give them access to everything. We need to give access to the necessary routes and only the necessary routes. And BGP gives us this flexibility. Now, there's lots of cool things that we can do in BGP. For example, we can tag a route in BGP, add a community to it or add something to it. And for you software developers, this is going to make more sense to you. But let's say, for example, we just wanted to tag the top, we wanted to tag a route with something. Maybe we called it a community. We can put a community over here. We can call it community cat. We can call it the cat community. I got Cindy the cat. She's really cool. We'll call it the cat community. And over here, you know what we're going to do? We're going to create another one called the dog community. More of a cat person, but you know, I love dogs, love cats, but whatever. I like anything with fur or feathers. So now let's do the same thing on the over here. We'll tag this route with a cat community, and then we'll tag this other route with a community called the dog community, a cat community, dog community, whatever. We'll call our routes whatever we want to call them. And that what we can do is we can set a policy in our data center that every time it sees the route coming with tag community, change the local preference or change or raise the weight. And every time you see a route coming with dog community, lower the rate. So this is where we start getting scalable as architects. We design ways to basically mark the routes, something, and then we can create a policy on the far end to look at the marked routes and do something about it. So this is where we're talking about communities. So let's think about how elegant this is. I can create a community that says, I can give you my routes, but you can't send the routes to anybody else. It's called no export. And AWS sends that. So what we're really dealing with kind of here is, and exactly here, it's like storing a variable. So when we're dealing with BGP, we've got a lot of places to tune things. So now there are. Now, if you guys want, we're here, we're doing good. Do you guys want to walk through on the difference between eBGP and iBGP and why organizations use both? If you do, type AWS BGP in the chat box. And then I'll know that you guys are looking for some more networking stuff. Because if it's networking and we're having fun, I don't mind teaching some other stuff while we're all here. I just want you guys to all have an incredible career. So I hear from Pierre, he wants some more AWS BGP. If I get at least 20 people to type in AWS BGP, we'll deal with a little more BGP. We'll give you guys some extra BGP skills. When I make it, you know, I've dedicated 4 hours for you guys today, and I'm willing to give it as much as it takes to really get you some lessons. We've done some really good traffic in terms of we've gone through much more than I was hoping to do at the speed that we were able to do these things. Okay, so there's a few of you guys. Caroline's recruiting Ronald McRae. I can do some more BGP. I want to make sure there's enough of you, the guys that want it, so that I'm not just like shoving BGP knowledge down people's throats because Mike likes BGP because I've been a network engineer since.
I think Caroline's making a joke about, you know, Meta is Facebook. She's saying Facebook needs to come to the session.
I think Facebook probably does need to come to this section. I will tell you this from experience. As many years as I've been in networking, if I know 100 people that truly know BGP properly in the entire world, it's probably a lot. Now, I understand that I may know 100. There's probably about 5,000 that know it, but it's that small of a knowledge base.
Looks like we got a question while we're waiting on.
Let's ask her the questions before we do there.
Yeah.
Okay, so the question is question on the ISP connection to each other. Can we assume all big ISPs are fully connected to each other? Generally speaking, yes. And maybe some mom and pop ISPs are connected to only up to one. Mom and pop ISPs are always going to be connected to several ISPs. It may only be 2 or 3, but they'll always be connected to several. One connection is a single point of failure. They'll typically be connected to several. But all the big people are pretty much paired with each other. So the answer is yes. And Tom Orpheus, for real, I've been a network architect for 25 years. I've interviewed 4,000 networking professionals. Of the 4,000 people that I've interviewed, I was able to hire 8 of them. 8 of them actually knew routing and switching. The rest of them honestly didn't know anything about networking. They were certified, but they were not knowledgeable. It is really, really, really hard to find a good network engineer. And it is even harder to find a good network architect. And when you can find them, they are worth their weight in gold. So I got to say, networking is the foundation for everything. Literally, when I did my CCIE 20 some years ago, about 3 million people had attempted the exam back when it was a 2-day exam. The people that started the Cisco process, and my number is 7417, they actually started counting at 1028 because it was 2 to the 10th. So of millions of people that started the certification process prior to me 20 some years ago, I was the 6,400th guy to actually pass it. So there was that. And that was back when it was a 2-day CCIE exam. It's gotten much easier now that it's a single-day exam, and the pass rate's gone through the roof. Now that you don't have to necessarily read 75,000 pages and take a 2-day test. Still a strong test, and it's great for everybody, but things have changed a little bit. So now that we're going back to some of this BGP content over here, let's walk through it. Chris, do you remember the thing that I was going to describe on BGP?
No.
Oh, IBGP and EBGP and
Oh, yeah.
Now I remember. Okay, thank you.
I was about to say IBGP and EBGP, but I was like, I don't know if that's specific enough.
Excellent. Now I can remember. So let's work through this, everyone. I want you guys to truly understand. This is what all architectures are going to look like for all networks, all interior service providers. So Pierre, if you just know networking, you're totally differentiated. I don't think you need that much more. Being competent itself is just a way to differentiate yourself, Mark. So let's go deal with this here. So let's look at a normal organization. Let's look at their systems. They typically have a core of their network. What is the core of their network? It's going to be really high performance routers. So let's say you've got a core of the network, and let's make sure in the core of their systems are 2. We're going to make it a really small core. So we've got room to blow this up for you guys. We've got an R3. We've got an R4. Now, this is the way all well-designed systems in the world are designed. These are the Cisco and Juniper recommendations. So typically speaking, you've got a core, and your core has very fast, really, really, really high-performance routers. Routers are computers that just calculate and forward traffic all day long. And these could be 100 gig links, and there's probably multiple 100 gig links between these devices. So what we're going to do is we're going to put multiple 100 gig links here, maybe in some link aggregation groups, things like port channel, ether channel, whatever term you choose to call it. Then, because it's the core, we want to make sure you've got ultimate availability. So we typically speaking, we'll fully mesh our core to make sure that we don't have any single points of failure. Now, typically speaking, this is considered the core of a network. This is where your performance is. You've got nothing here other than shape, size, and position. I think we can send this to the back. Position. Well, maybe not. Okay. Anyway, so that's the core of our system. And then typically what we have is we typically have another set of routers / switches, and this is going to be called the distribution layer. And then typically speaking, these distribution layer switch routers will typically aggregate into 2 locations. So, and then what we'll have, and I'll show you why we do this so that you understand how we promote high availability and why we do this. And then you typically have things called an access layer. And what we'll do is we'll feed the access layer switches into our distribution layer switches, which then get fed into the core. Now, here's why we do this. When you're making a 3-tier web architecture, you're decoupling it, right? Why are you decoupling things? Why do we ever decouple things? Because if anything happens here, we don't want the stuff here to know about it. So by creating an access layer, if something happens or goes haywire in this one switch, chances are it won't affect this switch or this switch. But if it does, which it shouldn't, it'll be blocked at the distribution switch. And if it doesn't get blocked at the distribution switch, it'll be blocked before it hopefully is isolated here. If not, it's going to be isolated here. It's less likely to affect here and here. So when we're dealing with network architecture, we're dealing with the decoupling. Wait, web architecture, load balancer, web servers, load balancer, app servers, queuing system database, maybe some caching, maybe some read replicas. Why are we doing all this decoupling? Because it enables us to do one thing in one part of our systems, and whatever we do in one part of our systems works in another part of our systems. Cindy, you want to come up here? So anyway, so that's why we're doing these things. That's why we're decoupling. That's why we're modularizing for scalability. So now let's look at what this is going to look like.
And Mike,
typically speaking,
before we get too deep, we have a really important question that we need to address.
Let's answer it. Let's answer it.
What's
what a
between
question.
a switch and a router?
What is the difference between a switch and a router? So Noel, this is a great question, and in today's world, it's very blurry. In the world where I come from, it's not so blurry. So a router operates at layer 3. And what do I mean by layer 3? A router basically goes from subnet to subnet to subnet. So everything on a router has 2 arms, one subnet, another subnet. And routers route between subnets. Switches, by comparison, are layer 2 devices. They operate at the data link layer. So a router forwards based on subnet, and a switch forwards based upon MAC addresses. So switches operate at layer 2, routers operate at layer 3. So when a packet hits a router, and this is pretty important, Noel, the router does a lookup. And it says, destined to this subnet, go out this interface. And if it doesn't have a route in the routing table, Noel, you know what happens? The router just drops the packet and it dies. And that's what's supposed to happen. By comparison, a switch is a layer 2 device, so a switch forwards on MAC addresses. So switches have no routing, they have no IP addresses, and everybody in the switch, or at least the virtual switch, can talk to each other, where every interface on a router is logically isolated, and you have to route between subnets. So when you're dealing with a switch, and I always get asked this question, so I always keep a switch directly next to my desktop. I'm going to rest it on my head for a minute. What happens is, let's say you've got let's pick one of these ports. Let's say you've got a user here. The router says, who has the MAC address for IP address 192.168.1.1? It'll flood it out every port in this switch. And then when this guy over here says, I have it, what'll happen is it'll put address in the MAC address table of the switch, and it will send data only out the port that's destined for that switch and nothing else. So switches operate at layer 2, and routers operate at layer 3. So switches forward based upon MAC addresses. Stretch my neck out after resting some metal on it. And routers operate based upon IP addresses. Now, Noel, when I say switch, what happened was, first, there was the concept of routers that worked on subnets, and then there were the kind of concept on switches that worked only on layer 2. And then about 20 years ago, Extreme Networks was probably the first people to do it. They came up with the concept of a layer 3 switch. It was a switch that could do routing and switching all in the same device. And the way this would work would basically be, on a switch, you can group ports together. Let's go back to the switch over here. Let's say I wanted to virtualize this switch, and I wanted to turn the switch and say all these ports exist in one virtual switch, and then these ports exist in another virtual switch. What I could then do in these layer 3 switches, which are really routers, is I could literally say all these 8 ports are all in this one IP subnet, and all these 8 ports are in another IP subnet, and all these ports are in another subnet, and then route between them. So the practicality, Noel, in today's world of a switch and a router isn't that much different. Routers operate at layer 3, switches operate at layer 2. So that's the only main difference. But that is a really good question. So let's go back to this. And honestly, that was a really great question, Noel. Often these things, these access devices, are layer 2 switches, like that little pizza box that I had on my head. And the distribution layer switches are typically routers, or high performance switches that do lots of routing. And what happens is the routers stop the broadcasts because they limit the broadcast, and the routers enable you to do access control lists. Access control lists enable you to keep traffic out of your subnet. And routers enable you to traffic engineer your traffic and filter your traffic and do firewalls and things that are much more secure. So routers are basically what we're going to be using at layer 3. If there's an IP address, it's a router. If it's a MAC address, it's a switch. And that's why they're starting to be used interchangeably, but they're not technically. So now it looks like this. So typically speaking, an organization is going to have what's called an interior gateway protocol. So let's say they're using something called OSPF. It's probably the most common interior gateway protocol used in today's world. What'll happen is all these routers are going to identify. They're going to tell everybody they exist. They're going to be like, hello, 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 hello. And basically these routers will multicast to 224.0.0.5 and 224.0.0.6. I'm here. I'm here. Wake up. I'm here. I'm here. Wait, have we ever heard of this before? Like a keep alive in DNS, or a keep alive as in a load balancer? Where do you think it all comes from? It all comes from networking and heartbeats years ago. I'm here. Are you there? I'm here. Are you there? I'm here. Are you there? So these routers constantly identify each other. They're constantly saying, I'm here. If one of the routers disappears, they remove the routes from the routing table. They're like a GPS for your traffic. They consistently direct your traffic. Go here, go here, go here, and your traffic gets to this location. So here we do routing where if this link fails, this link's going to recalculate in seconds because it's internal. We want to recalculate fast. So here's the thing. If I want to do math, 2 plus 2 plus 2 plus 2 plus 2, it's either 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Now, ask me to do advanced statistics or calculus at that speed. Not happening. The more intelligent we need, the more control we need, the more tuning we need, the slower it gets. Why do you use network load balancers? Because they're fast. Why are they fast? They don't do a lot. They look at the TCP, UDP header, the destination protocol and port number, and that's it. Why do we use application load balancers? Because they're smart. They're tunable, but they're slow. So it's the same thing. The more intelligence we need, the more slow it's going to be. The less intelligence we need, the speed. In an interior gateway protocol, internally to an organization, we're optimized for speed and self-healing. When we connect to external entities like AWS, we optimize our protocols for tunability, security, and control. So I hope that makes sense. So now let's look at what it's going to look like. What do these organizations look like? How do they build their systems? Let's have a party with it. So what you'll typically have is you're going to have your organization. And inside of your organization, let's fill it up with no colors. So this is going to be you. This is going to be the data center. Maybe the cloud, I don't care. Cloud's no more than a virtualized data center. And if we had a good router that we could use in the cloud, we'd be doing the same thing. Oh, so we've got our happy data center over here. Now let's say we've got an organization. And let's say the organization needs really high performance internet routing. Let's say there's the internet. Let's think about this. If we really want good internet routing, there's about 10 internet service providers that cover about 80% of all the internet's customers. 10 of them. Now, what that means is if I connect to AT&T and a customer's website's on AT&T, if I'm on AT&T and the customer's website's on AT&T, guess what? It's not very far for me to reach the customer. Now, if I'm on AT and the customer's website is on Verizon, I need to take my systems to get to AT&T, and then somehow I need to get to Verizon. Well, either that goes by me connecting to AT&T, who's connected to Verizon, or maybe I jump on AT&T and they pass me off to CenturyLink, and then they pass me off to Verizon. That's the quickest way on and off their network. That could be, the way my traffic goes, but we don't really know. But I'll tell you this, The more internet service providers your organization connects to, the more likely you are to be within one hop. So when you're dealing with really high performance web apps, if you want to minimize the latency, if I'm on the NTT network as it stands, I've already got the country of Japan covered because I'm on their local network, for example. And content delivery networks help mitigate this a little bit. But if we're really talking about pure routing and dynamic changes, if I'm connected to AT&T, I get access to AT&T's customers on network. If I'm connected to Verizon, I get them. If I'm connected to Vodafone, I'm getting them. If I'm connected to CenturyLink, I'm getting them. By the time I'm done, I connect to Singapore Telco, BT, and a few other major telcos. I'm connected to the whole world. And my internet performance is almost as good as my private network performance because everything is on network, not traversing the internet the same way. So it would be pretty common to connect to multiple internet service providers. So let's say we are a major e-commerce site and we've got 10 gig connections to the internet, all across different internet service providers. No big deal. Lots of companies would do this. Now, do we think it's a good idea to put all of our internet connections on a single router? All 10 connections, all on a single router. Even if we're smart, even if that router has multiple power supplies and multiple control modules and multiple line cards, what happens if we've got everything we have connected to a single router, a single $500,000 router that's connected to 10 internet service providers, and something happens to the router? Can anybody tell me what happens to our internet connections if the router dies? Somebody tell me what's going to happen if the router dies in the chat box. I promise you, it's not going to be a great situation, and nobody's going to be happy. Single router connected to 10 internet service providers. Noel, exactly. Everything goes down if the router goes down. Everything goes down. So, not good. So we think maybe we should split it among 2 routers, everybody? Instead of 1 router? We need to split it across 2 routers. So now we've got router 1 over here, let's call it, that's got 5 internet connections across different internet service providers. Exactly, Bernard. We got a single point of failure. I don't like single points of failure. No single cloud providers, no single internet service providers, no single points of failure. That is not a way to design a system for anybody, anywhere, anytime. So now let's do it over here. Let's do this. Okay, so now we've got the internet over here. We've got router 1 over here. We've got router 2 over here. Each one of these guys is connecting to an external entity on the internet. What is an external entity? An external autonomous system. If we connect to an external autonomous system, is this external BGP or is this internal BGP? If we connect to external systems. So, Pierre, exactly. Noel, exactly. When we connect to these external systems, and connect to external systems, it's external BGP. So now I want everybody to kind of think about this. The routes that are learned on router 1. Router 1's connected to 5 internet service providers. Router 2 is also connected to 5 internet service providers. As it stands right now, does router 1 know any of the information that's on router 2? Does router 2 know any information that's on router 1? Like, for example, what if the best path to Go Cloud Careers the best path to gocloudcareers.com is through router 2 and this internet service connection specifically? Will router 1 know how to do that? Not yet. Exactly, B3 Collector. it has no idea. Router 1 has no knowledge of the routes on router 2. Router 2 learned it via external BGP. Now, I'm sure you got two routers in your network and they're running OSPF so they can reach each other, but router 1 doesn't know router 2's routes, and router 2 doesn't know the routes that were learned by router 1. So what do we need to do between these devices? Not only do we have to have network connectivity, we have to run internal BGP. So what is the point of internal BGP? Internal BGP carries your internet routing information to other routes inside your system. So by doing this, if a user's data gets sent and it hits router 1, but router 2 has the absolute best path to it, router 1 will know to send the traffic to router 2 on the way to gocloudcareers.com. By comparison, if router 1 has the best path to it, the traffic would come up, and even if it hit router 2 would hot potato the traffic over to router 1, and then router 1 would send it to GoCloud Careers. So what we're really doing these things is we're putting them in here and we're exchanging routes. And we need that internal BGP to do it because we're going to be taking in a lot of routes. We're going to be taking in like 750,000 routes or more from every internet service provider we deal with. So we're going to get millions and millions and millions of routes. That's what we're really talking about. So we're talking about some really, really cool environments and things that we can actually be dealing with to kind of let you know about it. And that's why we do it. So that's why we're dealing with eBGP to connect to external entities and iBGP to carry the load across our autonomous systems. So why? Now, if we just had a single router, now let's say we've got 7.5 million routes sitting on these routers. Now, could we just dump it into OSPF through something called route redistribution and then teach OSPF or EIGRP or intermediate systems to intermediate systems, all these routes? Well, if we did, what happens is we would break things because it's not that we couldn't take routing information from BGP and to put it into our interior gateway protocol like OSPF. The problem is the interior gateway protocols are not designed for this many routes and we can't filter things. So the point being is we actually have to choose a situation and choose a routing protocol for our needs. So with any other part of our architecture, here's what we're dealing with. What is right for us at the right time. That's really what we're talking about. So I hope that's kind of clear for you guys. So that's what we're dealing with, eBGP and iBGP. So now, what do these systems really look like? What does an internet service provider look like? Well, an internet service provider might have two routers over here, like we're dealing with, that are connected to 10 ISPs. Then they may have their networks themselves, and inside of their networks, they've got two challenges. Well, let's talk about the BGP challenges. So let's deal with this. Here's the last thing I want to talk about BGP. And why am I talking about this for BGP? Well, if you understand this with regards to BGP, you're always going to know what to do with regards to VPC peering and things like this. And you're always going to have head and shoulders and years and years and years advancement over everybody else. So let's get you here. So let's go here. Now, normally speaking, this is eBGP. So you've got your eBGP speaker, and your eBGP speaker is connected to your ISP. So this is eBGP on this link. Now, over here, this is your router that's connected to the ISP. Now, if router 1 tells router 2, and it will, over here, router 2, it's iBGP routes, and if everybody in the company knew, let's say they had a default route, and the default route is a route that looks like this, 0.0.0.0/32. That's your default route. That says, if you don't know where to go to router 2. and router 2 and router 1 have IBGP communications between them, for example, what you ultimately would have is you'd have your traffic here. For the default route, it would go to router 2. Router 2 will have learned the routes via router 1, and it will send it to its ultimate destination. And everything works perfectly, perfectly, perfectly. Now, where are things going to break? And I'm going to show you where things are going to break, and they're going to break real fast and real quick and real easy. So let's unbreak them. Now, let's pretend we have this. Let's say we've got router 3. And let's say, with regards to router 3, we decided it would be fun and a great idea to run IBGP in addition between here and here and between here and here. But IBGP is not transitive. So now, let's pretend this route, this default route, was in BGP, but it's not. And it was sent to this router, but it's not over here at router 3. Now, let's say that we've learned all these cool routes. The routes are passed via eBGP to router 1, and then the routes are passed to router 2, but they're not passed to router 3. Why does router 2 not pass router 1's routes to router 3? IBGP is non-transitive. That means the routes won't be sent more than one location away, which means router 3 will never know about any of the routes learned from the internet. So with IBGP, it's not transitive. So how do we fix non-transitive routing, everybody? Well, we do two things. Option 1 is we fully mesh our IBGP peers. So now we do an IBGP connection between router 3 and router 1. So now if router 3 needs to reach router 1, it knows what to do, and it also knows how to reach router 2, so we fully mesh them. So this is going to work perfectly, perfectly, perfectly as it stands right now because we fully meshed them. What do we do with VPC peering? We have two options. We fully mesh them or we do something else. Now I'm going to show you where this something else comes from. So when network architects like me will tell you that Transit, Gateway, and Cloud Hub are the same, and you deal with the AWS people that are not networking people, and they're going to look at them as so different. I'm going to show you why they're really just identical. I mean, they're all just a BGP route reflector, the same 30-year-old technology, and it's great technology and it works, and we've used it everywhere. So what ultimately happens in Ken, I don't know what you mean by MLSP. If you're referring to multi-protocol label switching or MPLS, that's something entirely different. But that's something different. We're talking about BGP right now. I can and will do an MPLS day if anybody wants me to in another day. But now we're really getting out of IP routing and we're now getting into label switching. And a lot of that MPLS stuff is going to go away when we're dealing with cloud computing. Their cloud providers are all going to be running it internally. So let's keep you guys, But if you guys want, I'm happy to do an MPLS day. I've worked on MPLS for a quarter of a century and always thrilled to talk about it. So now let's bring it back. So if we have this, if we have ISP, let's make it look a little more elegant for you. So now it's going to look more familiar. So now we've got over here, let's call it our router. Now let's say over here, got another organization. Let's call it a router 2. And let's make a router 3. R3. R4. Now in this particular information, let's look at what we actually have going on here. So now let's assume we have connectivity between these organizations. Now let's go back to our transitive routing. We've got another router over here. This router connects to the internet, R1. Let's call this R25. My numbering was goofy. Now let's connect the internet. So R25, let's call it the internet. Let's say R25 has two connections that are BGP. Now, we're probably not going to put them all on a single router, but let's just pretend we are for right now. Now, what you have, because this is our router and that's the internet, that will always be considered to be eBGP. Now, if we send these routes over here via iBGP, in a perfect world, this router over here, this R1, would send the internet routes to R2 and to R3 and to R4. And if that occurred, R2 would know to go to R1 to R25 out to the internet. And R2 would know how to go out to the internet. And R3 would know how to reach R2 through R1 if the routing information was passed from here to here to here. So that's realistically what's working wrong. So is the networking needs to go from here to here. So now let's think about this completely. If router 1 was told, take router 2's routes and share them with router 3, and router 1 said, take router 4's routes and share them with router 2, and everybody shared everybody's routes, everybody would be talking. But iBGP, as part of its loop avoidance strategy and non-transit strategy, doesn't allow transitive routing. And what does that mean? It means that the routes learned that are pushed to router 1 won't be sent to router 2. And it means that if router 2 tells router 1 about some routes via iBGP, router 1 won't tell router 25, and it won't tell router 3. So nobody knows about anything. That's why it's non-transitive routing. Now with BGP, we can fix that. We just call this device router 1, we call it a route reflector. And then we specify all these devices as route reflector clients. And by doing that, what we're really doing is we're telling router 1 to take router 2's routes and pass them to router 3, and take the routes learned by router 25 and send them to everybody else. And now once we turn this into a route reflector, what we have? We've got transitive routing. No longer have to fully mesh our BGP peers. So now, let's change everything. Let's get rid of this internet service provider. We don't need it. Let's get rid of this eBGP pairing to the internet. We don't need it. Now, you're on the cloud. This is your VPC. Life's good. Everything in your VPC is working perfectly. You got your web apps, you got your business apps, your ERP systems. Everything's going good. Business is great. Everybody's making money. Life is good. Everybody's fine. And now you decide that you're going to purchase 3 other companies. They're all one company. And this new company that you buy has a New York office, a San Francisco office, and a London office. And guess what? You just want to connect them to your VPC. So now we've got New York. Now we've got San Francisco or San Jose. And now let's say London. You all connected them to your VPC. Now, guess what? New York sends its routes to the AWS VPC. The AWS VPC and New York can talk to each other. San Jose sends you its routes. You send San Jose your routes. You can talk to San Jose and life's good. Now, London sends you their routes. You send London your routes. Life is good. We're having a party time. Everybody party at Mike's house. I'm now talking to the folks in New York. I'm talking to people in San Jose, and I'm talking to people in London. Everything's great, right? Well, what if New York has to talk to London? They can't. What if New York has to talk to San Jose? They can't. Why can't they? We have non-transitive routing. What does non-transitive routing mean? It means the routes that are set from New York to here aren't set to San Jose. So what are our options? We have 2 options here. Well, it's the same 2 options we have with BGP. The identical 2 options. Nothing changes at all. So I'll show you what I mean. Here's option 1. Option 1 is simply do this. Let's get everybody talking to everybody. We've got 4, let's say we've got 4 VPCs, and you want everybody to talk to everybody. we can what's called fully mesh them. So let's say we took the VPC here, the VPC here. This is option 1. Click, connect, peer here, peer here, peer here, oops, peer here, peer here. Now everybody can talk to everybody because we're fully meshed. Now, this is great for 4 devices. But what happens if we've got a lot of devices? So let's break this down. We're dealing with this formula, and the formula is going to be called n times n minus 1 divided by 2. So that means if you've got 3 VPCs that need to be paired, or 3 IBGP pairs, it's the same thing. It's going to be 3 times 3 minus 2, or 3 times 3 minus 1, which is 2. So that gives us 6 divided by 3 is 3 pairing connections. Now we've got 4. 4 times 3 is 12 divided by 2 is 6 pairing connections. But now we've got 10. 10 times 9 divided by 2 is 45. As you can see, it gets very big very fast. And we can only deal with 125 VPC pairing sessions on AWS. So you're not going to be able to do that many. So in BGP, we have this concept of a route reflector. If this is the route reflector, all the routes that are sent here will be sent here, which will be sent here. In the cloud, we have the same concept of a route reflector. We don't call it a route reflector. We've got this concept called Cloud Hub. So what is Cloud Hub? If New York has a VPN in, and San Francisco has a VPN, and London has a VPN, we terminate the VPNs on Cloud Hub. We tell Cloud Hub basically you're now a route reflector, and we tell Cloud Hub to reflect the routes learned from New York to San Jose back to London and vice versa. Everybody's routes are sent to everybody. By reflecting everybody's routes, everybody's talking to each other, and we've taken non-transitive routing and called it transitive routing. So in the network world, here's what we call it. It's called a route reflector. In AWS, we call it Cloud Hub. Then AWS looked at it, and here's what they said. Not everybody can get away with a VPN connection. What if we need guaranteed performance, guaranteed throughput? Then we need a private line. So now how would we use a private line? We'd use a private line in the following manners. We would, for example, use something called, instead of Cloud Hub, we're going to call it Transit Gateway. What is the difference between Cloud Hub and Transit Gateway? Not a whole heck of a lot. It's pretty much the same thing. But Transit Gateway works with private lines and VPN connections. So realistically speaking, that's what we're talking about. We're talking about the same thing, the same concept. And that's why I want to make sure that everybody truly gets this. It's the same concept. So now who has questions? Does anybody have any questions for me right now? Because we've covered a lot. We started with IP addresses. After we went from IP addresses, we talked about IP addressing. Then we talked about Transit Gateway. Then we talked about Cloud Hub. All of these things are AWS services. Since we can't go there, Pierre, and then put one of our VPN concentrators there, and we can't put one of our routers things there, we're now in a position where everything is virtual. Everything is virtual. So since you guys asked, you got about 20 minutes. Let's do it. It'll round out your networking knowledge. I don't know how we did this at a subnetting workshop, but you guys were all learning good. You guys were all fast. So we can talk a little bit about what is MPLS. So let's do it. So what is MPLS? Normally speaking, you got a device that comes into your network, and this is what your routers do. Your routers have a bunch of interfaces.
Mike, can you confirm the formula again?
It's n times n minus 1 divided by 2.
Okay. Sorry, someone asked for just to verify. So.
Okay, sure.
So n times n minus 1 divided by 2. Okay. Thank you.
You got it. So going back to this particular environment, a router's got multiple interfaces. So it's going to have an interface over here, and it's going to connect to another router. It's going to have a subnet over here. This router is going to have a LAN segment on it. which, generally speaking, we draw like this. And then let's say on the server, let's say we've got a server that's got an IP address of 1.2.3.4. That's the server's address. And let's say we're over here, we're popping here at 192.168.1.1, which makes the router's IP address, which is our default gateway on the same subnet, a 1.0. Let's say that over here, I don't want to really think about anything too complicated. Let's say we've got 10, let's just 1.0.0.1/30. That's being used on one side, which then means the .2 is going to be used on the other side. What'll ultimately happen is when this packet gets into this router, and the goal is to reach 1.2.3.4, if this is your system is going to say, do I have a route to 1.2.3.4? And your computer has a route table, and it's going to look at its route table, and it's going to say, no, but I have a default gateway, and my default gateway is 192.168.1.0. So you send your packets directly over to here. That's where you're sending your data. So you send your data to the router, and the router's here, and the router now says, the packet then looks up, and the router says, do I have a route to 1.2.3.4? And the router says, I do. Go out this interface. So then the router sends the packet out this interface on this WAN link, and now the packet sits in this router. And this router says, hey, do I have a path to 1.2.3.4? And the router says, in my routing table, I have a directly connected subnet 1.2.3.0/24. So what happens, the router sends that packet out this interface. And the router will then send what's called an ARP broadcast, which is who has the MAC address for 1.2.3.4. And then what will ultimately happen is 1.2.3.4 will reply to the ARP. And it will say, I have the MAC address. And then 1.2.3.4 is going to answer. And it's going to then say, do I have a route to 192.168.1.1 to answer Mike's query? And it's going to look in its routing table, and it's going to say my default gateway is 1.2.3.1.24, and it's going to send its packet to the router. Now the router is going to look in its routing table and say, do I have a route to 192.168.1.0? And it's going to say, yes, go out this interface. And when the router's here, and the router's going to say, do I have a route to 192.168.1.0? And it's going to say, yes, I do. And it's going to send an ARP broadcast. Who has the MAC address of 192.168.1.0? Going to send it to this guy. This guy's going to respond, and then a session is going to be established, and our traffic will be bidirectional, and that's how it's going to occur. Note, all of this happened based on destination subnet mask. So destination subnet mask, that's it. We routed everything based on subnets. So what is MPLS? Instead of routing on subnets, let's say we've got 4 routers. Router 1, router 2, router 3, router 4. So in this particular environment, we build our 4 routers. We create our links in between our routers. And we enable our interior gateway protocol, just like before. Let's say we're running our OSPF. And now we turn this into our own sort of like cloud. So let's fill this. We'll send it to the back. There's a way to send this to the back, right? Send it back. Okay. So now in our MPLS network, now we've got an environment. So first we turn on our OSPF, our interior gateway protocol. Then instead of switching packets, we turn on a label distribution protocol or a tag distribution protocol. It's another routing protocol. And in this case, I'm just going to type TDP, LDP. There's lots of protocols that were used for this. And then we're going to have to signal these things. We're going to create a series of tunnels. We're going to use something called RSVP. And then what we're really going to do is we're going to come up with a primary path, which is going to look like this. We're going to explicitly tell our network, this is the best way to go through. the network, and then we're going to create a backup path. And we're going to call and say, this is the backup path of the network. So now what happens, we're going to send our data from this R1. It's going to hit the cloud. But when it hits the cloud's going to smack a label on it. So normally when we talk about 802.1q tagging, we talk about smacking an 802.1q tag on it. Here we're going to smack a label on it. So we're going to take our packet, we're going to pop a label on it. The routers are then going to switch based on labels. They're going to stick this packet into this traffic engineered tunnel, which is then going to go to router 3. Router 3 is going to see the packet and say, got it, but it's now destined to an IP subnet. That router 3 will then strip off the label and send it out its port to go on its merry way. So what is MPLS really? Instead of switching based on packets and the destination packet, we just switch based on labels. What is a label? If I take my phone over here and I put my phone inside of a box and I ship the box via FedEx, and the person on the far end takes the phone out of the box and then picks up the phone and uses it, that's what's happening. When we use an MPLS network, all we really do is we take the packets, we smack a label on them, we then switch the packets from switch to switch based upon the labels, and then when they get out of our systems, we pull the labels off. It's like taking our phone out of the box, and then we place our phone call. So that's really all that we're talking about over there. So, that was way out of scope for this, but, people asked the questions, and I wanted to see what we could do to make everybody happy. I want to make sure everybody truly gets a truly amazing experience. So it's 4:38. I said I would run till 5. So do you guys have any questions? If you do, let's answer your questions, because I want to make sure we give you a good experience. So bear with me. So Asim, can we have certain locations reflecting the routes while other locations refrain from it? Could you set up some devices to be route reflectors in clients and others not? The answer is absolutely yes. And you definitely would. Asim Hans. Also, in a specific router location, can we control the reflection of certain subnet blocks, while some would allow others? So either you're going to be a route reflector client or not. Now, anytime you're dealing with any kind of peering sessions, you've got a lot of flexibility, distribute list, route maps, filters, all kinds of ways that you can actually tune what you actually send and where. So the answer is you've got lots of flexibility in policy-based routing. You could be dealing with BGP. I mean, I could fill up books with all the tuning you could actually do. Here, I said I was switching using the tag. How would it be switched otherwise? Okay, so typically speaking, going through the system normally, we're going to switch based upon destination IP address. Router is going to look at the destination subnet, and it's going to send it that way. In this case, we're switching based upon labels. Really, it's just an encapsulation. And all of what we do is really an encapsulation. We want to send Ethernet signaling over MPLS. We're just taking one thing, sticking it in something else, and taking it out the far end. So GRE tunneling, take a packet, stick it inside of a tunnel. IPsec tunnel, stick it inside of an IPsec tunnel. Any of these things, we're just switching based upon another path. So that's really all we're talking about. But great question there, PR. Truly, truly, truly great question. MPLS is just another form of encapsulation and de-encapsulation. That's all it is. It just takes an IP network to do it. But that's all it is. Okay, wonderful, Pierre. I'm so happy you got that. Perfect, Asim. Asim, I'm very happy you got it. And that's why we're doing these things. I truly, truly, truly want to get you guys to do it. So while people are asking final questions, if you guys had a good time, if you can hit the like button, it kind of helps signal the algorithms to let other people know we're doing a good job. And we really try to work hard to provide as much training as we can for the community. Actually, could you let us know where you're from? I always love to see where you guys are from. Let us know where you guys are from in the chat box. I find it truly amazing sometimes because we've got some people that I've seen from all over the world. Alonzo, my good friend, I'm good to see you here. Tom, we're curious where you're from. You look like you've got a similar name to me, so I'm always kind of curious. Alonzo, you're in Katy, Texas. Tom in the Netherlands, fantastic. Pierre in Montreal, that's wonderful. B3 collector. Pierre, I'm so happy. Alonzo, Tom, excellent. Kenya, this is really wonderful. Montreal, Ireland, Sydney. Oh, this is just so nice.
I wonder what time it is in Sydney.
Raleigh, North Carolina, Kenya, from the south, 101 from the south. I know something about being in the south. I'm in South Florida. Caroline, Raleigh, but from Kenya. That's really great. Omar Farouk, Austin, Texas. Wow, this is just so nice. Amarath, I know you're in Toronto over there. Seema's in India. That's great. Bernard, you're from Cameroon in Virginia. That's fantastic. Kenya's from Atlanta, but you're going to go back and watch it a few times. You know what? In the beginning, 20 some years ago, I think it took me about 10 times going through the subnetting. And you know what? I got it. So whatever it takes to get it is just an important concept. And I try and run these periodically because I think it's so important. I love the sunglasses there, Ken. So thank you all. Honestly, it's been a true honor and a true privilege spending the afternoon with you. If you have any other questions, let me know now. Otherwise, on Monday, please register. Chris from my team is gonna pop it there. So happy, Caroline and Kenya, Carl. If it takes a few times, it takes a few times. Evo, and I know that's your name, but I've been calling you that for a long time, and I think you're amazing. So I'm so thrilled you were able to participate. Any last questions for me? Otherwise, please join us on the Monday call. My team's got a couple more videos. Since everything we do is about getting you cloud hired, I'm going to give you some special video that's coming out tomorrow that's going to improve your chances of getting hired. Everything we do is about helping you get cloud hired. So I want to thank you all for this great time we spent together, and I look forward to seeing you in another video. Andrew, so nice to see you. Alonzo, always appreciate it. Fantastic, everyone. Take care, everyone. See you very soon.